Poštovane dame i gospodo, predstavnici medija i učesnici, dobrodošli na konferenciju Nuklearna sigurnost danas. Konferenciju o primjenama izvora zračenja i nuklearne energije koju ove godine organizujemo u virtualnom formatu. Pandemija koronavirusa i najava energetske krize u sinergiji otvaraju danas neka nova pitanja o nekim manje ili više poznatim temama. Između ostalih, ove godine je problem potencijalne energetske krize aktualizovao i neizostavno pitanje nuklearne energetike kao jednog od najčistijih i najekonomičnijih izvora električne energije, ali koji istovremeno sa sobom i dalje nosi veliki strah koji je posledica prethodnih akcidenata. Naime, upravo su ove godine obeležene godišnjice dva najveća nuklearna akcidenta, onom u Černobilju pre 35 godina i u Fukušimi pre 10 godina, o čemu je bilo reči na dva jednodnevna skupa održana 11. marta i 26. aprila kao uvodni deo ove konferencije koja se održava 2. decembra. Svi zainteresovani mogu da prate i aktivno učestvuju u konferenciji putem live streama na YouTube kanalu direktorata, kao i preko zvaničnog sajta konferencije. Gledaoci koji nas prate putem live streama svoja pitanja za današnje govornike mogu slati na mail press@srbatom.gov.rs, a mi ćemo se potruditi da ih tokom razgovora postavimo našim učesnicima. Vreme je da otvorimo današnju konferenciju. Pozivam Slađana Velinova, direktora Direktorata za radijacionu i nuklearnu sigurnost i bezbednost Srbije i koordinatora za vezu sa Međunarodnom agencijom za atomsku energiju, da vam se obrati. Izvolite.
Uvaženi gosti, poštovani panelisti, dragi kolege, želim da vas pozdravim ispred Direktorata za radijacionu i nuklearnu sigurnost i bezbednost Srbije na trećoj konferenciji Nuklearna sigurnost danas. I poželim dobrodošlicu i uspešno učešće na ovoj konferenciji. Prošlo je godinu dana od prethodne konferencije, a čitav svet se i dalje nalazi u borbi protiv pandemije koronavirusa. Dok vlada neizvesnost u vezi novih talasa i sojeva, želeli smo da odvojimo malo vremena i kroz današnju konferenciju našem stanovništvu i stručnoj javnosti prikažemo trenutne aktivnosti, dostignuća, aktuelnosti, ali i zanimljive informacije u oblasti primjene nuklearnih tehnologija, radijacione i nuklearne sigurnosti. U godini, čijem kraju se bližimo, direktorat je uspeo da i u produženo vreme pandemije nastavi da svoje delatnosti obavlja nesmetano, obezbeđujući na taj način adekvatnu kontrolu delatnosti. Sa ciljem zaštite izloženih radnika, lekara, medicinskih tehničara, pacijenata i stanovništva od štetnog dejstva ionizujućih zračenja, ali i izdavanja dozvola za uvoz i korišćenje kako nove opreme za COVID bolnice, a u koju spadaju rentgen aparati za snimanje i za kompjuterizovanu tomografiju, tako i oprema za dijagnostikovanje i terapiju drugih bolesti, kao i radiofarmaceutika neophodnih za dijagnostiku i terapiju najtežih bolesti. Pored 3 laboratorije za brzu detekciju koronavirusa koje je direktorat kroz mehanizme tehničke saradnje sa Međunarodnom agencijom za atomsku energiju obezbedio prošle godine, ove godine obezbeđena je još jedna takva laboratorija za Veterinarski specijalistički institut iz Niša. Ova oprema, vrednosti veće od 70.000 evra, omogućit će ne samo proširenje kapaciteta za brzu detekciju koronavirusa uz visok nivo sigurnosti za ljude koji rade u laboratorijama i njihovu okolinu, već i mogućnost njenog kasnijeg korišćenja i u drugim oblastima gde je potrebna brza i pouzdana detekcija uz visok stepen sigurnosti. Pored navedenog, direktorat ulaže velike napore na obezbeđivanju nabavke novih brahiterapijskih jedinica kojima će se obezbediti pravovremena i efikasna terapija najtežih bolesti kod pacijenata. Ovu godinu obeležili su i 2 godišnjice. 10 godina od akcidenta u Fukušimi i 35 godina od akcidenta u Černobilju. 2 događaja koji su imale veoma veliki uticaj ne samo na nuklearnu energetiku, već i na druge oblasti primjene nuklearnih tehnologija. Direktorat je ove 2 godišnjice ispratio sa 2 skupa koji su naišle na veoma pozitivan prijem. Edukacija kadrova nastavljena je zbog izazovne epidemiološke situacije kroz virtualne mehanizme i ove godine. Međunarodna agencija za atomsku energiju obezbedile veliki broj virtualnih obuka, omogućavajući tako njihovu dostupnost bez potrebe za izlaganjem riziku od dobijanja koronavirusa. Napomenuo bih i da direktorat kroz mehanizme saradnje sa Evropskom komisijom i Međunarodnom agencijom za atomsku energiju ulaže značajne napore da podigne nivo spremnosti za delovanje u slučaju vanrednog događaja, kao i da poveća kapacitete za ranu najavu radijacionog ili nuklearnog akcidenta. U prilog u ovome govori uspešno učešće direktorata i drugih institucija Republike Srbije na međunarodnoj vežbi Konvex 3 ranije ove godine, a tokom koje je simuliran akcident na nuklearne elektrane u Ujedinjenim Arapskim Emiratima. Rezultati ove vežbe pokazali su da je naša država raspolaže adekvatnim merama za odgovor u slučaju jednog ovakvog događaja bilo gde u svetu. Za kraj želim da vas sve pozdravim i poželim da sa ove konferencije ponesete neka nova saznanja koje ćete sutra moći iskoristiti za opštu dobit svih.
Hvala gospodinu Velinovu. Nuklearna energetika biće tema prvog panela na kome će danas eksperti iz međunarodnih organizacija izneti svoje stavove u korišćenju nuklearne energije, njenoj ulozi u globalnoj ekonomiji kao i o sigurnosti nuklearnih postrojenja. Na samom početku panela obratit će vam se Jan Haverkamp, viši stručnjak za nuklearnu energiju i energetsku politiku pri Svetskom informativnom servisu za energiju i Greenpeace Holandija, a suosnivač je i potpredsednik Nuclear Transparency Watch. Pogledajmo prezentaciju gospodina Haverkampa.
Welcome to my home in Hallingen in the Netherlands. My name is Jan Haverkamp, and I'm going to give you an overview of what the position is of the organizations I work for on the issue of nuclear power. I will now share my screen. As I said, my name is Jan Haverkamp. I'm an academic engineer from the Netherlands. I'm now 62 years old and senior expert nuclear energy and energy policy for the organizations Greenpeace and the World Information Service on Energy, also known as WISE. I am the vice chair of Nuclear Transparency Watch, an organization based in Paris and Brussels that oversees transparency in the nuclear sector. I'm working 40 years on these issues all over Europe and the wider world. I worked from the mid-1990s also in Romania, Bulgaria, Serbia, and the wider Balkans. I worked for 4 years in Brussels on the formulation of the Nuclear Safety Directive, the Nuclear Waste Directive, and during the Fukushima catastrophe at the Greenpeace EU unit. I lived for 21 years in the Czech Republic and Poland, and I'm now based in Amsterdam in the Netherlands. In Europe, but also worldwide, nuclear energy is an industry in decline, and very little people are really aware of that. Currently, there are 105 nuclear power reactors in the EU and 114 in wider Europe. From those, 57 are likely to close in the coming decades. There are currently 4 nuclear reactors under construction in the EU and 3 more in wider Europe that at least could come onto the grid in the same time. That means that in the coming 10 years, nuclear power in the European grid will decline with more than 25%. From the current fleet, I would estimate around 5 reactors may still be operational in 2050. Now, this decline is putting the industry into large problems. There is a large gap in the needed decommissioning funds. That means a gap between the money that is there and the money that needs to be there at the moment of decommissioning. There is a large gap in the funds needed for waste management. The European Commission estimated that gap to be over 500 billion euros. There is a lack of new in-stream of skilled people to deal with decommissioning and waste management. Of course, if the industry is in decline, it also means declining revenues from operation and ongoing losses due to slowly declining electricity prices because of the market entrance of cheap renewable power. The nuclear industry knows this and is desperately trying to turn the tide, but times are not on their side. The nuclear industry will not help solving climate change. When the nuclear industry would like to double its capacity in Europe before 2050, it would need to install around 190 new large nuclear reactors within the coming 29 years. If they would go for extreme lifetime extensions of aging reactors, and of course with the attached risks, this could maybe be reduced to 150. Because in the coming 10 to 15 years, we will only see 6 to 8 new reactors coming online, it would mean that every year between 2035 and 2050, there would have to come between 7 and 12 new reactors to the grid every year, year on year. And that comes from a base of less than 1 reactor per year currently, with an average current construction time of 14 years, including preparation. Now, that is very unlikely, and it would only cover around 20% greenhouse gas emissions from the electricity sector. That is less than 8% of the greenhouse gas emissions compared to business as usual. For that, construction would need almost 1 trillion euros of capital investment. That same sum invested in energy efficiency, combined with renewable capacity, building on an already changing grid system, would yield double to triple the amount of greenhouse gas emission reductions. The conclusion is nuclear power, nuclear energy is too little, too late, and too costly to be relevant for climate policy. But there are more reasons to phase out nuclear power, and that are nuclear's legacies. Nuclear accidents do happen. Whereas the oldest nuclear power stations would have a chance of less than once in 1,000 reactor years on a nuclear meltdown, and current reactors only once in 1,000,000 years, most operating reactors, by the way, once every 10,000 years. We have witnessed already 25 meltdown incidents over the last 70 years, from which 4 resulted in the necessity of large-scale evacuations, thousands to tens of thousands of casualties, widespread radioactive contamination, closed zones for many decades, and multi-hundred billion euros in economic damage. Such accidents cannot be excluded in the future, not from the aging existing fleet, nor from newly constructed reactors. And any severe accident in any reactor will, besides that, have severe consequences for the entire fleet, which will need to be updated and upgraded after every accident happening. Then there is the nuclear waste problem, especially that of high-level radioactive waste. After already 70 years of research, this has not been solved. Even projects for deep geological disposal in Finland, Sweden, and France are facing tough technical challenges that have yet to be resolved before any of these can get its safety case passed. An increase in use of nuclear power will inevitably lead to an increase in nuclear weapon proliferation. The IAEA, even before it became a blatant nuclear power propaganda organization under its current president, Grossi, could not prevent nuclear weapon programs in Israel, South Africa, Argentina, Brazil, Sweden, Pakistan, India, North Korea, Iran, Iraq, and Libya. Some of these have been closed down. Others are still causing daily headaches. New developments and designs come too late and pose more of the same problems. The nuclear industry is fiercely looking for ways out of this situation, among others by proposing cutting costs by delivering factory-line produced small modular reactors and new reactor designs that would address part of the safety and waste problems. However, small reactors appear not to be cheaper than the current generation of new reactors because of the capital needed for the buildup of construction infrastructure and loss of economies of scale. Light water reactor types, PWRs and BWRs, made small but still evaluations of the current designs, do not solve the problems with risks, security, and waste. New designs may reduce some of the high-level wastes, but they don't completely erase the problem and create larger amounts of short-lived wastes that still need to be kept out of the environment for hundreds of years. What is worse is that each of these newer designs is a proliferation nightmare, playing reprocessing technology into the hands of whoever operates them. Oh yes, and there will not be commercial small reactors available before 2035, and then we talk about the light water reactor type. New designs not before 2040, if ever. Nuclear energy is furthermore in no way clean or sustainable. The production of radioactive waste is a dirty legacy for future generations, and the pollution caused by uranium mining and larger nuclear accidents are the main reasons why nuclear energy does not fulfill the do no significant harm criteria in the EU Directive on Taxonomy for Sustainable Finance. The fact that it depends on limited uranium stocks makes it also non-sustainable. Were nuclear to be taken up in the taxonomy, business finance has already indicated it would make the taxonomy worthless as a tool. Still, there is attention for nuclear energy in Serbia, but this is a diversion from urgent climate action. Serbia looks at the PAX-2 in Hungary and shady plans for small nuclear reactors in Romania, or even at own nuclear capacity. The PAX-2 nuclear power station remains politically controversial, not only because it is built over a seismic fault line and constructor Rosatom appears not to be able to submit sufficient quality documentation for the go-ahead of construction. Romanian SMR plans follow on failed attempts to finalize the Cernavoda 3 and 4 reactors with first European and then Chinese help. The current flirt with NuScale will not see reactors going online before 2035, given the experimental status of this PowerPoint reactor. And I call it a PowerPoint reactor because these reactor types, the new designs, but also the small nuclear reactors, at present only exist on paper. Also, the NuScale reactors will not come cheap. Building own capacity will confront Serbia with the same problems as these Hungarian and Romanian projects. It would not deliver any electricity before 2035, if ever. In the meantime, there will be high hesitance from the investor community to invest in alternative electricity capacity or in new technologies needing electricity. Investors will wait and see. Nuclear power is old thinking in Europe and worldwide. Urgent climate action is needed today, now, in industry, in building and infrastructure, in agriculture, in mobility, in consumer activity, and in the energy sector. Nuclear power is nothing more or less than an irrelevant distraction. Nuclear power is not necessary. It constitutes less than 3% of primary energy use. An increasing amount of scenarios, several already featured in the IPCC SR 1.5 report and since updated, shows that a fully decarbonized energy system in 2050 can not only run without nuclear power, but it is even cheaper, delivers faster, and puts less strain on the environment and future generations. Serbia's future lays in an increase in energy efficiency, its enormous renewable potential, and a move to sustainable industrial, agricultural, and mobility practices, not in nuclear power. I hope I've been able to explain to you why nuclear is not the future. The future is to be clean and renewable. If you have further questions, I'm available to answer them. Thank you very much.
Hvala gospodinu Haverkampu na zaista sjajnom izlaganju. Pozivam sada doktora Jonathana Cobba, višeg menadžera za komunikacije pri Svetskoj nuklearnoj asocijaciji, da nam predstavi svoje izlaganje. Gospodine Cobb, izvolite.
Hello, I'm Jonathan Cobb, Senior Communication Manager at World Nuclear Association. I would like to offer my thanks to the Directorate for Radiation and Nuclear Safety and Security of Serbia for inviting me to speak about my vision for nuclear energy, today and tomorrow. Over the past 2 years, we have all been reminded about the fragility of life in the face of the current pandemic, and to appreciate more deeply what our world has to offer. And it is the way in which people have taken action to protect themselves and others, and the way in which the global scientific community has innovated at a pace far faster than many thought possible, that has given me greater hope that we can successfully overcome an existential threat that has challenged us for far longer: climate change. Unlike the pandemic, the solution to tackling climate change is simple. We must reduce the amount of greenhouse gases being released by human activities to near zero by the middle of this century. If we don't, and we allow temperatures to rise by more than 1.5 degrees Celsius, the impacts on climate will not only threaten the fragile web of our global ecosystem, but also humanity's ability to grow and prosper within it. Technology advancements have brought many benefits and improvements to our way of life. Economic growth, industry, travel, and in particular, energy production have helped enrich the lives of many. But these advancements have been powered by burning fossil fuels, producing the greenhouse gases that threaten not only our global environment, but also our economies and our lives. And there are many more people who have yet to fully benefit from the advancements fossil fuels has helped provide. They have every right to aspire to the same standards of living that the most fortunate, the most privileged of us currently enjoy. My vision for the future is where we build on the proven capabilities of nuclear energy as one of a broad suite of clean, low-carbon technologies, not just for electricity production, but as a way of achieving net zero emissions across the entire range of human activities. It is a vision where we protect our environment from climate change, but also provide abundant energy so we can continue to progress and ensure that all benefit from the fruits of such progress. In order to look at what nuclear energy could do for the future, it is important to know what it is doing for us today. The first reactors for electricity production started in the mid-1950s, but it has only been over the last 40 to 50 years that nuclear generation has taken off globally. Today, there are 441 reactors operating in more than 30 countries. There are a further 56 reactors under construction. Together, the 395 gigawatts of nuclear capacity supplies more than 2,500 terawatt-hours of electricity each year, meeting more than 10% of the world's electricity needs. And nuclear does this with very low greenhouse gas emissions. No form of electricity generation, be it nuclear, solar or wind, is completely free from greenhouse gas emissions. But study after study have shown that, even when the full fuel cycle is considered, using nuclear to generate electricity is among the closest to carbon-free. Another benefit of nuclear energy, when compared to many other low-carbon energy options, is that it is able to generate electricity with much greater reliability. This reliability and improved performance of nuclear reactors is something that has been gained through more than 50 years of reactor operation. In the 1970s, fewer than 3 reactors in 10 had capacity factors over 80%. In 2020, nearly 7 in 10 reactors achieved this performance level, even as some reactors were being asked to operate at lower capacity factors to incorporate variable renewables. Now let's be clear, although a wind turbine is dependent on the strength of the breeze and a solar panel on the amount of sunshine, it is undoubtedly the case that a broad range of different electricity generation sources will be needed in a clean energy mix. And nuclear will have an important role to play in providing a reliable foundation to provide flexibility for such a generation mix. Already in France, for example, nuclear reactors are varying their output to provide the system flexibility needed to incorporate more generation from solar and wind. And future reactor designs will be even more flexible in varying their output or redirecting it to other uses. But reliable baseload generation will be a mainstay for the majority of reactors for many years to come. Given that, it is reassuring to note that the performance improvements seen from decades of experience of nuclear generation apply to all reactors, not just those built more recently. Analysis of the performance of reactors from those that have come online most recently to those that have been operating for more than 50 years shows that the oldest reactors now perform at the same high standards as those constructed more recently. It is this record of performance that has resulted in reactor operators applying to continue operating reactors for up to 80 years. Indeed, for the 3/4 of the world's reactors still under 40 years old, it is likely that many have yet to reach the halfway point in their potential service life. This means most of the current fleet of reactors should have a significant role to play in achieving net zero in 2050. But while the current reactors have an important role to play, new reactors will be needed to replace fossil fuels and meet future electricity demand growth. So far in 2021, we have seen 5 new reactors start up in China, India, Pakistan and the United Arab Emirates. And we have seen construction start on 7 new reactors in China, India, Russia and Turkey. With more construction starts and grid connections, the pace of new reactor build is increasing. But to make the contribution needed to tackle climate change effectively, the pace of future construction must increase. And it is to my vision of nuclear and its role in a clean energy future that I will now turn my attention. But first, let me set out what are the needs of a future energy system. As I highlighted in my introduction, access to electricity brings huge benefits and demand is growing. But the threat of climate change demands we move rapidly to a clean low carbon mix that still provides ample energy for all. In addition to the threat of climate change, it is already the case that fossil fuels, particularly coal, have a huge negative health impact today. And for those reasons, although nuclear generation is a key component of clean energy supply today, a much expanded role will be needed to achieve the global environmental and sustainable development goals of the future. In 2021, nearly 1 billion people still don't have access to electricity, and many more do not have access to reliable supplies. While we seek to improve energy efficiency to help reduce greenhouse gas emissions, the expectation is that electricity demand will continue to grow globally, with increasing demand driven by the still increasing population and by economic development, to provide all people with a better standard of living. Meeting the needs of these billions of people is one of the key United Nations Sustainable Development Goals. These people should have every right to expect that they can light their homes so that their children can do their homework and gain a better education. And they can run household appliances like a washing machine to reduce the drudgery of domestic chores, a burden that still unfairly falls disproportionately on women and girls. And we must achieve these goals while at the same time rapidly decarbonising our energy system. Some progress has been made. Current policies have started to phase down greenhouse gas emissions, but now we must rapidly transition from the start of phase down to a full phase out. I was at the COP26 Climate Change Conference in Glasgow, Scotland, in November this year. Undoubtedly, the global resolve to tackle climate change was as strong as ever. For the first time, governments agreed to the phase down of coal-fired generation and phasing out of fossil fuel subsidies, and to increase efforts to deploy low-emission energy and clean power generation. Contributing to this, we saw France and the UK commit to develop a new generation of reactors, and partnerships between countries such as the USA and Romania to deploy new small modular reactors. But still, the commitments made at COP26 would only result in a global temperature rise significantly above 2 degrees Celsius, far too much. Much more needs to be done to limit climate change to a more manageable 1.5 degrees Celsius. The climate drivers to phase out coal to tackle the long-term threat of climate change will bring other health benefits much sooner. Globally, the air pollution from fossil-fired power plants is estimated to contribute to the premature deaths of more than 800,000 people every year. And it is not just coal. When we look at both the impacts of accidents and air pollution, as well as the greenhouse gas emissions of different energy sources, it is clear that for a safer, healthier energy future, we must transition away from the combustion of carbon in its many forms to clean energy from nuclear, hydro, wind and solar. This is my vision of a future energy system. So how are we doing so far? Well, despite more than 2 decades of action on climate change, the share of fossil fuels in the global electricity generation mix has barely changed, with more than 60% of electricity still generated from coal, oil and fossil gas. The picture looks even worse when we look at the absolute amount of electricity produced from different sources. With global demand for electricity increasing by around 70% in the last 20 years, the amount of electricity generated today from fossil fuels is more than the total electricity demand in the year 2000. Progress is far too slow, and we need to expand the use of all low-carbon generation. How are things in Europe? Here the picture is a little better. In 2021, about 60% of electricity generation came from clean, low-carbon sources, with nuclear the largest single source of electricity, providing more than 25% of Europe's electricity. Nuclear's role in electricity generation in Europe varies from country to country. Some countries don't have their own nuclear power plants, although some of those are considering using nuclear in the future. However, others have made nuclear the cornerstone of achieving the kind of low-carbon generation mix that the rest of the world will be trying to achieve over the next decades. In the mid-1970s, France made the strategic decision to transform their electricity generation mix, meeting rising demand with a rapid expansion of nuclear generation capacity. This was done before climate change became such an international issue. Instead, with few fossil fuel reserves of their own, the motivation for France to focus on nuclear was to avoid future price spikes and security of supply issues of the type caused by the 1970s oil crisis. France was not alone. In Sweden, early increases in electricity demand had been met with an expansion of their hydro capacity. But from the mid-1970s, a decade of expansion of their nuclear generation capacity resulted in a low-carbon mix predominantly powered by similar levels of nuclear and hydro generation. Now, nearly 50 years on from those oil shocks of the 70s, a new wave of supply shortages and skyrocketing price rises are bringing the same concerns to the fore for more countries. Now, the same economic structure that means nuclear is not subject to the same impacts of fuel costs as fossil fuel gas generation also means that a significant component of the cost of new nuclear is the capital cost of the reactor. It is essential to maximise the contribution of new nuclear generation. Therefore, we need to unlock low-cost finance for nuclear projects, as well as optimising the nuclear regulatory sector and ensuring a level playing field with other low-carbon technologies. It is important these conditions are met because new nuclear generation offers a competitive, low-carbon solution, particularly in OECD countries. And extending the operation of existing reactors, long-term operation, offers the most cost-effective method of generating additional low-carbon electricity. Making sure we get the most out of our existing fleet of reactors brings many benefits in addition to low-cost, low-carbon electricity. Long-term operation provides shovel-ready jobs, generating employment in refurbishment and the decades of extended operations thereafter. It preserves valuable know-how and provides important benefits for local and national economies. But as well as preserving employment for communities with operational nuclear reactors, we should also consider the impact of efforts to decarbonise electricity generation on communities hosting fossil fuel plants. Those plants will have provided jobs to those communities, potentially for decades. A just transition must provide opportunities for local communities that have been supported by fossil fuel plants. New nuclear build can provide such opportunities. Replacing large capacity fossil power plants with large capacity nuclear power plants offers local high skilled employment opportunities for decades. A community switching from coal to nuclear would regenerate jobs and improve the health of the local environment with reduced air pollution. The small footprint of a nuclear plant in comparison to other low-carbon generation would preserve open spaces, and the investment would help stimulate the local economy. The last part of my vision for the future of nuclear is to look beyond traditional uses of electricity. 2 years ago, the small community of Pevek in northeast Russia started to receive electricity generated by 2 small reactors aboard the Akademik Lomonosov, the world's first floating nuclear power plant that had been purpose-built. The reactors are capable of supplying not only electricity, replacing the local fossil fuel plant, but also district heating and fresh water. In the future, small reactors, and in particular small modular reactors, will be able to supply low-carbon electricity to communities too remote to be connected to a large-scale grid. Together, small modular reactors and the latest generation of large-scale reactors will be able to increase the range of applications to which nuclear technologies can be applied. There are a variety of different SMR technologies under development, of which these are just a selection. High-temperature reactors, such as the HTGR being commissioned in China, are of particular interest, with the potential to provide process heat for industry. One application would be to generate hydrogen through thermochemical processes. Hydrogen can also be generated by electrolysis using current pressurized water reactor technology. Hydrogen has great potential as a clean fuel for transport, for industrial use and home heating. By utilising technologies available today and in the near future, nuclear has the potential to do much more than decarbonise our electricity grids. It can heat our homes, power our industry and provide clean fuel for transport. But more importantly, it can enable us to continue to benefit from all the myriad of things that electricity has allowed us to enjoy, and to make those benefits available to everyone, while helping we ensure to protect the world we live in. That is my nuclear vision, my vision for today and tomorrow. Thank you for listening.
Hvala gospodinu Kobu. Bile su ovo dve odlične prezentacije i prezenteri koji su se potrudili da iz svojih uglova prikažu ulogu nuklearne energetike u današnjem svetu. Za kraj ovog panela vidjet ćemo ovu sliku iz trećeg ugla. Agencija za nuklearnu energiju Organizacije za ekonomsku saradnju i razvoj već 7 decenija služi kao svojevrstan forum svojim državama članicama za pomoć u održavanju i daljem razvoju kroz međunarodnu saradnju, naučnih, tehnoloških i pravnih osnova potrebnih za sigurno, ekološki prihvatljivo i ekonomično korišćenje nuklearne energije u mirnodopske svrhe. Pozivam doktora Michela Bartelemija, analitičara nuklearne energije pri Agenciji za nuklearnu energiju Organizacije za ekonomsku saradnju i razvoj, da nam održi svoje izlaganje.
Good morning, colleagues. It is my distinct pleasure to address you virtually through this recording to participate to your annual conference. Of course, we have very much liked to have the opportunity to join you in person, and I hope next year this will be possible. Today, I'm going to talk to you about the future of nuclear energy, its key challenges and opportunity, sharing with you some key insight from recent work of the OECD Nuclear Energy Agency. For those of you who don't know us, we are an international agency, part of the OECD, based in Paris, that bring together 34 countries seeking excellence in nuclear safety, technology, and policy. We offer a forum for collaborations and also for joint activities in these areas. We also increasingly develop relationships with industry, university, and civil society through specific mechanisms. Together, NEA countries operate more than 80% of the world installed capacity today. The way we work traditionally is through different committees that you can see on this slide. And as you can see, the breadth of work activities cover key areas for the development of nuclear energy, from nuclear safety, waste management, decommissioning, radio protection, legal affairs, and nuclear science. I represent the Secretariat for the Committee for Technical and Economic Studies on Nuclear Energy Development and the fuel cycle that does most of the work that relates to the long-term outlook of nuclear power. I'm going to share with you today some key insight from some work we published a few days before COP26, and that look at the role for nuclear energy, broadly speaking, toward net zero objectives and the key policy issues that need to be tackled in this field. And they start with a very strong warning that many have raised in Glasgow, that the world is not on track, that if we look at pathway from the IPCC in terms of CO2 emissions and climate outcome by the end of the century, many of these lead to rise in global average temperature well above 2 degrees Celsius. And if we look at what we think about our carbon budget, how much CO2 emissions can we emit by 2050 to still be on track with respect to the Paris Agreement, in particular 1.5 degrees scenario, we only have about 8 years at current rate of CO2 emissions. So there's a very strong sense of urgency for the 2050 objectives, but also and especially for finding solutions for reducing CO2 emissions in this decade in order to be in a pathway feasible to meet the objectives of the Paris Agreement. When we look at the role of nuclear energy in reference pathways, those developed by the IEA from a number of international players in this field, from large energy corporations, from think tanks. The key findings from these studies is that in all of them there is a growing role for nuclear energy that has on average to more than double by 2050. In some pathways, in particular, if we look at the 90 pathways that the IPCC reviews in its latest report, we see more than a tripling of installed nuclear capacity. And so clearly there is a growing role for nuclear power to contribute to the Paris Agreement objectives. But if we look a bit more in detail at these pathways, which we did, what we see is that they primarily rely on existing nuclear technology, being existing reactor in operation or gigawatt scale Gen 3 reactors under construction and sometimes in operation. But they overlook the role and potential of nuclear innovation, be it in terms of innovative new reactor design, small modular reactors, advanced reactors, or the role of innovative applications of nuclear energy through nuclear heat for district applications, for industry, through nuclear hydrogen, or through desalination. And so what we wanted to do at the NEA is to start to quantify what could be the full contribution of nuclear power toward climate change. Of course, we very much respect the views in each country with respect to the development of nuclear energy. But it's important that policymakers can have all the facts on the table in terms of the potential of different technologies before formulating energy policy decisions. And in particular, here I present nuclear energy, but when we look at other parts of the energy system in these decarbonization pathways, what we do see is that there are very, very aspirational pathways for, let's say, variable renewable, for storage, for energy efficiencies. And these have a purpose because it helps policymakers to focus their mind. But at the same time, they have views on nuclear, which ultimately are somewhat conservative because they don't take into account the potential of nuclear innovation. And we see that as a gap in the analysis for informing policymakers' decisions, and therefore a role at NEA to help fill that gap. I'm going next part of my presentation to tell you a little bit about how we see full potential of nuclear toward net zero. And then I will be moving to another part of my presentation where I will be focusing more on how to formulate policies that allow us to get there. And in that respect, on the importance of when we think in particular in terms of cost, not only looking at cost at the plant level, but really taking a holistic system level view on the cost of decarbonization. And we see that at NEA as essential for formulating efficient policies for decarbonization. So on this slide, you can see what we see as the key pillars for nuclear energy to contribute to net zero. And unsurprisingly, you can see different technologies, existing, new reactors, small modular reactors, and also different applications through hydrogen or heat application. And all of them can be looked together in a complementary way to understand the potential of nuclear energy. I will start with long-term operations, and I wanted to say a few words about where things stand in terms of the economics of this low carbon solutions. And then I will share with you the overall findings of our analysis, where we will take a conservative and aspirational view on the potential for these different nuclear blocks to contribute to net zero. A key message on existing nuclear from the work we do with the International Energy Agency is that it is by far the most competitive low carbon solution that countries have at hand when they operate existing nuclear capacities. And this is something we find with great robustness across our member countries. That doesn't mean that sometimes the economics is not changing, and it's not so much that the costs are high, rather is that electricity markets can sometimes be dysfunctional, obsolete, and they fail to recognize the value that existing nuclear power plays toward the system in terms of reliability, in terms of contribution to climate reductions. So putting that together, we see an important potential for long-term operations if we are able to address some of the changes with current electricity markets. Moving on to the second block, gigawatt scale, gigascale new build reactors. This is an area where we've been looking very carefully at the cost at NEA in recent years, trying to, in particular, the questions that many policymakers have in mind. What happened with first-of-a-kind Gen 3 reactors? What have costs increased so dramatically? And what are the perspectives in terms of cost reduction? And an important message on this from NEA that I want to stress with you today is that we do see from the work we do once again with the IEA that if there has been significant inflation in the cost of these technologies over the last decade, we do start to see cost reduction perspective in sight, which shows that some of the changes that nuclear sector has faced in recent years were specific to building first-of-a-kind demonstration units, and that, as equally important, the industry today is able to learn from these challenging projects to then improve efficiency and therefore lower costs, and in such an outlook, a positive outlook, we also see an important contribution of large Gen 3 toward decarbonizations. But the one for which things are far from being written or set in stones is probably small modular reactors. This is a nuclear conference, so you will all be familiar with the subject, with the technology, and its benefits. The point I would therefore stress for you is on the applications of this technology. Because when we look at those, we see in many cases that small modular, in most cases I should say, that small modular reactors are expected to open new markets for nuclear energy. And that makes projecting, forecasting, the market, potential market of such technology very, very challenging, because you're starting from scratch, and you essentially introducing what will be destructive technology in existing and future energy markets. And in that sense, we very much see small modular reactors as complementary to large reactors, because they will serve different energy market needs. And you can see here some key applications that range from on-grid power, particularly for replacing coal power plants, to off-grid for remote site, which could be remote communities, but also remote mining sites in particular. We also see emerging discussion with respect to merchant shipping, and last but not least, and very importantly, for heat, in particular for industrial processes, which we know are going to be hard to abate energy sectors, and therefore it's essential that we focus very much on these sectors for saying how nuclear can help contribute to the decarbonization. And I will finish before putting together some consolidated numbers with nuclear hybrid energy systems, which for us includes heat and hydrogen, but in that then, will be vectors or in the energy sectors, and then of course can then be linked with a lot of different applications. In case of hydrogen, can be linked with other molecules, and therefore help to deliver a range of products. But as much as this is a very, very complex field, we see that if, in particular when it comes to hydrogen, if the perspective of the hydrogen economy materialize, we see that there is a serious case to be made for relying on nuclear power to deliver large-scale, low-carbon hydrogen. Of course, renewable, valuable renewables are a solution at hand that also have some merit. We don't want to discount them, but we see that nuclear power that produces today competitive electricity that can operate with high capacity factor, that deliver very large-scale infrastructures, ticks all the boxes for really a scenario where we have very large-scale deployment of hydrogen. In particular, if we think as hydrogen for some industrial applications, we really see clear merit for nuclear power, and this will also be something that ultimately will drive the three pillars I have previously introduced, and so we can see that all the different type of reactor systems can contribute to producing large-scale hydrogen productions, and also to some extent heat applications, which is also something where we see important prospects for hard to abate sectors, as I have already explained for small modular reactors. So this is the point where I put all of these things together, and where I start to quantify what would be the full potential contribution of nuclear toward net zero. And when we do that, we combine what are conservative, which are the solid blocks here, and the aspirational, which are dashed, perspective for long-term operations, large-scale Gen 3 reactors and small modular reactors that will produce both electricity and this non-electric application. And when we put all of this together, we will see that nuclear will almost triple by 2050, and will avoid more than 87 gigatons of cumulative emissions between period from today to 2050. Talking about gigaton might not speak of CO2 emissions, might not speak to everybody. To put this in context, by 2050 we will see nuclear that could support avoiding nearly 5 gigatons of CO2 emissions annually, and that's equivalent to the current emissions of the overall US economy. So as you can see, this is very significant potential contribution of nuclear power by 2050. And the last bit of information on this slide, on this graph, is that this will be a contribution in line with the average of the IPCC scenarios. In the short time I have left, I will now spend a little bit of time to talk about how to develop pathways that will get us there. How do we chart an affordable path to net zero? This is something for which we need to introduce some concepts on the cost of electricity. When the cost of electricity is usually discussed in energy policy discussions, it tends to focus on the plant level. And there are very good reasons for that, and this is where a lot of the cost are born. The issue when we do that is that we will fail to appreciate the importance of integrating different technologies to the mix, and the fact that at the system level, the level of the grid, there are costs that can vary significantly for integrating different technology, in particular different low carbon technologies. And so it's important for us to really make this dichotomy and take this cost into consideration when we chart a path for decarbonization of a given economy. And in addition to that, it's important to take into account social and environmental costs, which in this case will include the cost of climate change. So I'll talk about system cost, but I think it's useful to go a step further so that you understand where this cost at the system level are born. And in fact, we see three areas that we model in our work at the Nuclear Energy Agency. The first part of this cost are very much to do with transport and distribution of electricity, where variable renewable can have higher cost because of the way they are spatially distributed. Second, an important cost will be what we call balancing cost, that is related to the fact that variable renewable, wind, solar, will comes intrinsically with higher uncertainty in generation, which means the system will need more margins to deal with this uncertainty. And third and last, we have what we call profile cost, which I think are sometimes best called backup cost, which means that when the wind is not blowing and the sun is not shining, you're going to need to have something else in the mix in our electricity system to manage this intermittency, and so the additional plant will have some costs that need to be taken into account appropriately. We model at NEA this system cost, and you can see here represented in a three-dimension chart, which shows you a different level of variable renewable from low to high, different level of carbon emissions, and different level of variable renewable from low variable renewables to high variable renewable, different level of carbon constraints from a low carbon constraints of 400 grams per kilowatt hours to a net zero carbon constraints. And last but not least, the impact on the price of electricity. What's important here we go, is to then link this with the carbon constraint we have by 2050 and the carbon constraint we have by 2030. In 2030, this is represented on the green line. In 2050, this is the red line. And quite quickly, we can start drawing some pathway together there. And by 2030, with a 50 gram of CO2 carbon constraint, we see a lot of pathway possible. And some countries may decide to have very high renewables in the mix and may be willing by 2030 to pay a premium for that. The problem is, if we only do that, we put ourselves on the path dependency. And we pass ourselves in a path dependency where it can quickly become unachievable to meet the 2050 targets, because we built the systems allowing ourselves for a small premium by 2030 without necessarily realizing how much prohibitive will be meeting scenarios with a very high level of variable renewables, and where we won't allow gas or any form of fossil fuel to meet the intermittencies. And unfortunately, because that's something we see very much today, because sometimes countries over-focus on the 2030 objectives, they may have the tendency to chart such a path. And this is why we very much advocate at NEA to not only take a system approach to these issues, but take a very long-term view when thinking at our climate objectives, and in some ways, could simply put, think one step ahead for planning to net zero. And by doing that, we can then chart a path which can get us to 2050 at a much more affordable cost for society, at least one that will not be prohibitive, considering what our models tell us. And so essentially, this is about, maybe in closing, being able to chart a path that we find balance, mix between variable renewables and nuclear energy in order to meet the objective of the Paris Agreement. Of course, this is for every country to think about which pathways they prefer. But once again, policymakers do need to have all the facts in order to make informed decisions. And this is what we do at NEA through our studies in this field. And so with that, I thank you for your attention, and thank you again for the invitation. And I look forward to future opportunities to discuss these important issues with you. Thank you.
Hvala gospodinu Bertelemiju na zaista sjajnom izlaganju. Jedna od najznačajnijih svetskih tema poslednjih godina je zagađenje životne sredine, sa posebnim osvrtom na zagađenje mora i okeana, koji odavno već predstavlja veliki problem za čovečanstvo. Poguban uticaj plastičnog otpada i mikroplastike na živi svet mora i okeana odražava se negativno ne samo na ove ekosisteme, već i putem lanca ishrane na celokupno čovečanstvo. Prema analizama svetskih studija očekuje se da će do 2050. godine u svetskim okeanima biti više plastike nego ribe. S tim u vezi, Međunarodna agencija za atomsku energiju je kao organizacija koja okuplja veliki broj zemalja članica od ove godine inicirala program pod nazivom NUTEC Plastics, kako bi se obezbedila kontrola plastičnog otpada uz definisanje nuklearnih tehnologija za reciklažu plastike, koje će obezbediti pretvaranje plastičnog otpada u upotrebljiv resurs, o čemu će govoriti stručnjaci Međunarodne agencije za atomsku energiju u drugom panelu ove konferencije. Sa nama su danas gospođa Selina Horak, šefica odseka za radioizotopske proizvode i radijacionu tehnologiju Odeljenja fizičko-hemijskih nauka Međunarodne agencije za atomsku energiju i gospodin Mark Metjan, istraživač u radioekološkoj laboratoriji, Laboratorije za životnu sredinu Međunarodne agencije za atomsku energiju, da održe izlaganje ispred Međunarodne agencije za atomsku energiju. I would like to invite Mrs. Selina Horak and Mr. Mark Metyan to give insight of the EAA activities in field of environmental protection. Mrs. Horak, the floor is yours.
Thank you very much, and I will share my screen. Can you see it well?
Yes.
Thank you very much. First of all, I would like to thank the organizer for this invitation and the opportunity to share with all of you the IAEA initiative in controlling environmental pollutions with radiation science and technology. My name is Selina Horak, and I work at IAEA as head of the radioisotope product and radiation technology section. So IAEA has a strong mandate to contribute with atomic energy to peace, health, and prosperity throughout the world. And this is implemented through the three main pillars IAEA has: safeguard, verification, safety and security, science, and technology. You may be quite familiar with the nuclear power activity, but we also promote and accelerate the non-power application for strengthening science and technology to member states. And this is one of the topics of our speak now. In this field, the Department of Nuclear Science and Application and the Department of Technical Cooperation interact very closely to implement the proper mechanisms to implement this kind of activity. And these mechanisms are related to the five main fields of activity that our Nuclear Science and Application Department has in the non-power nuclear applications: food and agriculture, human health, science and industry, water resources, and environment. To conduct all this activity, IAEA has different mechanisms depending on the required needs: coordinated research project for R&D, pilot scale plans, technical cooperation project at the national, regional, and interregional level, also for capacity building and technology transfers, and regular activities such as scientific conference, side events at the general conference, and so on. And now, what are we doing in the field of environmental application? We know that it's becoming increasingly clear that humankind's environmental problems are no longer merely local or regional, but have become continental in scope. Economically and technically feasibility technology for controlling pollution from gaseous emission and liquid effluent streams are being sought by technologists working in a variety of areas, including radiation technology. Radiation technology is quite effective for remediation of contaminated environments. When irradiated with high energy radiation, practically all the energy absorbed initiates the ionization and excitation to result in formation of free radical and molecular species to destroy or to convert the harmful chemicals. Over the last few decades, extensive work has been carried out on utilizing radiation technology for environmental remediation. This work includes the application of radiation technology for simultaneous removal of some toxic flue gases, wastewater treatment, and hygienization of sewage produced in agriculture. And recently, we adopted existing technology used for polymer modification to contribute and to modify plastic waste to generate valuable products. And here you can find an example of research coordinated product we are now ongoing to strengthen the activity on this main field of how radiation can contribute to pollution controls in the area of how to treat the wastewater for reuse containing organic pollutant, for removal of some organic pollutant in the waste by radiation. And of course, recently we have launched this new CRP on recycling of polymer waste for structural and non-structural material. Now it is my pleasure to outline very briefly what the IAEA offers as nuclear solution to plastic pollution, this NUTEC plastic. The objective of NUTEC plastic is to assist the IAEA member state in integrating nuclear and nuclear-derived techniques in their effort to address challenges of plastic pollution. NUTEC plastic builds on a portfolio of IAEA research and technical cooperation projects around plastic recycling using radiation technology and marine monitoring of microplastic using isotopic tracing techniques. NUTEC plastic positions the IAEA on an important issue of global concern, the plastic pollution. To spread the voice, IAEA has organized 4 roundtables around the world in the 4 regions, having high-level participants and experts sharing experience. In May, we start in Asia-Pacific regions, then in the Americas, in September for Africa, and the last one for us in October for Europe and Central Asia. Now let me start by giving you a feel for the scale of the challenge of plastic waste. Why we have started with this NUTEC plastic. Plastic are everywhere and has some great characteristics. We all know about that. However, this advantage also causes high plastic usage and disposal of plastic waste generate environmental problems. Because of the durability of plastic, discarded end-of-life plastic are accumulating. Around 4% of world's oil and gas production is used as feedstock to make plastic, and a further 3 to 4% to provide the needed process energy. Around half of all plastic produced each year is used for single-use or short-lived products. Only a small portion of plastic generated are recycling, very, very low. Around 9% is recycling worldwide, and 12% is incinerated, adding to carbon emission and draining resources. Around 60% of the near 8.5 billion tons of plastic ever produced has landed in landfills or been discarded in the environment. More than 100 million tons of plastic have ended up in our oceans, and the amount is increasing, unfortunately. That is why everyone are aware that the situation is clearly not sustainable. So now I will refer to the technology innovation we are proposing to mitigate plastic waste, how radiation technology can contribute to recycling of plastic waste. So this is an image to illustrate the plastic value chain and the 2 approach NUTEC plastic has to controlling plastic pollution with advanced technology and monitoring the marine microplastic. I'm going to refer to how ionizing radiation can modify structural material with polymers and contribute to mechanical or chemical recycling methods that are the conventional existing methodology for recycling of polymers. Then the question naturally arises, what can we do? The answer is reduce the volume of plastic waste, of course. One way you can reduce plastic waste volume is by reducing single-use plastic. Another is by improving plastic waste recycling. The IAEA is making its contribution to reducing plastic waste, in particular to the technological areas shown in red, creating sustainable, alternative, and innovating recycling. The IAEA is poised to provide unique nuclear solution to plastic pollution through development and promotion of radiation technology to help replace petroleum-based plastic with biodegradable ones to improve conventional recycling practice and to renew end-of-life plastic. So in this area of sustainable alternative, how we can provide some solution on that, radiation technology can be used to develop eco-friendly, sustainable alternative to petroleum-based plastic. Radiation is conventionally used as a catalyst for making plastic, it can be used for the manufacture of new biodegradable plastic. If you do this thing using bio-based feedstock, you can create biodegradable polymers to replace single-use petroleum-based ones. You can also use radiation to tailor the material performance to the target application, creating active packaging products. For example, this is just to illustrate one example that our researcher that contribute in our CRP has been developed is a biodegradable plastic that it is strained the property through radiation technology, and it is resistant to temperature. The IAEA offers also innovation of plastic waste recycling using radiation technology. This is the second approach. One is for sustainable biodegradable alternative, and this is for recycling of existing plastic waste. In brief, radiation can support and extend conventional recycling strategy by enabling better sorting of plastic, breaking down plastic waste into components, converting plastic into fuel and feedstock, and treating plastic waste to create upscale products, such as composite material. In the next few minutes, I will explain each of these in particular. Regarding how to sort this plastic, you can use radiation for high fidelity sorting of plastic waste pellets or flakes according to polymer types. Exposure to radiation will change the charge on the surface of the plastic, and this charge varies according to plastic type. This opens a means for sorting according to electrostatic charge on the plastic, thus making possible sorting of mixed plastic, but also improving the quality of the recycling raw material. This alleviates one of the major obstacles limiting the extent of plastic waste recycling, namely the inadequate sorting. Some polymers are quite similar in these characteristics, so alternative technology to help in sorting this plastic are very useful. And this is an example on how this works. This is a patent from Germany that has configured an e-beam facility for sorting different plastics, such as low-density polyethylene and polypropylene with a low dose to separate these very similar characteristic polymers. Another main obstacle in conventional plastic recycling is that repeated mechanical recycling lowers the quality of plastic pellets generated and thus limited the number of recycling plastic possible. You can use radiation to break down plastic polymer that no longer has sufficient quality into smaller components and use this smaller component to generate new plastic products. In this way, the plastic waste recycling life cycle is extended. So you are not going to recycling in the same way, but you are going to convert into a new recycling way. This is another application of radiation technology in plastic recycling that have some advantage that neither solvent nor additive are required, making it a great technology. And this is an example of a commercially available technology in the degradation, for example, of Teflon into very, very fine micropower. Radiation technology has a very advantage over other conventional methodology. Now, when plastic reaches its end of life, so there is no possibility for even other recycling process, chemical or advanced recycling can be applied to convert the plastic to fuel and feedstock. Chemical recycling is not used much now as it is an energy-intensive and expensive process. This is where radiation technology can help. If you combine pyrolysis of cracking of plastic with radiation in chemical recycling, you can lower the required process temperature by almost 100 degrees or more than save money. This green technology also delivers a high product purity and less byproduct or off-gas and solid residue. And this is an example in the next slide that can show some first preliminary configuration that some researcher, in the case is Mr. Alexander Ponomarev, has extended work on this topic, and it's very promising kind of application that ionizing radiation can improve the chemical recycling, lower energy, and also improving the kind of byproduct that are obtained through this technology. Now, end-of-life plastic waste can also be introduced into other products. This is well known. Often refer to a secondary recycling product. Conventionally, these have a lower value than the original. However, you can use radiation processing to tailor the plastic property and upscale the value of the secondary product to create novel and innovative material with a higher market value, but also with some improved characteristic. And this is an example also that has been provided by some researchers, the incorporation of polyolefin rubber into different materials such as concrete or asphalt. And in this case, the main advantage that radiation technology has is that it improves the interface adherence among the two phases, the incorporated plastic and the inorganic matrix of the concrete, for example. No, we are not going to have two separated phases that can generate some breaking material, and this improves the characteristic of this mechanical property in this case. So what is it about ionizing radiation? Which are the sources that we use to generate these changes? Ionizing radiation allows you to do all these wonderful things. Yes, don't worry if you are not a teacher. I will explain this in an easily understandable term. Ionizing radiation for radiation processing typically is generated by special equipment that generate E-beams, accelerated E-beams, or gamma rays. Examples of generators for both are shown at the left of this slide. Ionizing radiation works by creating reactive charges, species, both radical and charged ion, which lead to chemical reaction that you can actually control or harness by varying radiation, dose, and conditions. You can control the reaction to either break bonds between atoms, to break down plastic, or to join atoms forming bonds or cross-link to tailor the plastic property. This work in bulk material, but also in the surface. So depending on the application, which is the effect that we are going to try to tailor in order to get the final product. What are we doing now for our member state? Radiation processing using ionizing radiation is an established technology. What is new, it is the application to treat plastic waste. So we are adapting existing and very successful stories into this new application. We are presently developing and testing radiation technology for the range of application to treat plastic waste. As I had mentioned before, sorting, breaking down, converting into fuel and feedstock, and creating upscale products. Ultimately, this generates knowledge and develop technology that should be transferred to our member state. At the moment, the focus is in converting plastic waste into novel and functional materials. The R&D activity are on the laboratory scale, and scaling up of process is crucial. Therefore, our aim is to establish a plastic recycling pilot plant that is docked onto the conventional mechanical recycling facility. At the bottom of this slide, you see the schematic of such a pilot plant. The conventional mechanical recycling part is to the right in the boxes. The E-beam irradiator show is to be used to modify or tailor the property of plastic pellets generated in mechanical recycling, in one case specifically for integrating into construction material. The radiation assisting chemical recycling indicate is still under development, but the interest in this is huge. Recycling hard to recycling and mixed plastic. This is the main advantage that chemical recycling has. It can be used for mix of plastic. And this is the hard to recycle plastic. This is the main option that we are trying to explore and promote. We are hopeful that we can work with other stakeholders to realize pilot plans and eventually scale up demonstration plans. I look forward to further discussion of how we might join effort and concert effort to advance a unique nuclear solution to plastic pollutions. And why IAEA and what the IAEA can offer global membership and high legitimacy. So we have 173 member states that we can contribute and help and support to establish a good network of collaboration. We can establish this collaboration at the regional and international level. Of course, we provide a very neutral assessment on the research and the technology transfer. We are working with a network also of researchers at the academic, private sectors, and expert level in order to provide all this effort and share with the member state. We are a neutral organization that tries to promote all this in the more realistic ways for all the different member states that are requiring this kind of application. And finally, I have introduced to you the solution that nuclear technology offers to lower plastic waste volume and thus reduce the amount of plastic upstream that can reach our oceans. This is our missions in our side. But in the next presentation, Mr. Marc Metian will pick up where nuclear technology offers solutions to plastic pollution in our ocean in a downstream approach. So thank you very much from my side, and I will move to Marc in the next presentation. Thank you.
Thank you, Selina. My pleasure to take the relay on the presentation of our activity related to the downstream. I will share now my presentation, and I will give you some insights from Monaco. In the meantime, I would like to also thanks the organizer to invite us for presenting this. I think I don't have it right now. Just to give me a second. Okay, and my presentation is there. Can you see my presentation? I hope so. So yeah, so my part again. I'll come back to the basic. And again, good morning from Monaco, where we have our laboratories in marine environment. Nuclear application, as presented by my colleague, is a wide range of activities and including environment. And in this context, here in Monaco, we are focusing on marine environment, trying to understand and protecting marine environment. And all the activity we're doing, I will not go into new tech right away, but I would like to present all the activities we're doing. It includes marine pollution, of course, but also all the different topics where a range of nuclear and SOP tools or nuclear technology can understand and protect the environment. So marine pollution, seafood safety, and all the big change that the ocean is enduring right now. And this is for having the main target is to aim for having a healthy ocean, sustainable, to deliver a range of health and well-being benefiting to people. This is super important. Our ocean are critical for people. And of course, not only the people living on the coast, but also all the different countries rely on the benefit from it. As mentioned here in Monaco for the New Tech Plastic, the initiative, we are involved deeply, especially in terms of monitoring and trying to assess the impact of plastic on marine organisms or organisms in general, aquatic organisms. You saw in the previous presentation the solution for the upstream, which is super important, and you saw all it was well presented the way we, as the IAEA, are trying to tackle this problem. In terms of ocean, this is a different approach because there's a lot of things that we know, and there's a lot of things that still need to be known on this impact of marine plastic. Again, to put the screenshot. In the global initiatives, there's two main parts, and we are in Monaco focusing on enhancing the global understanding of the abundance and the impact of marine plastic pollution. How to do that? Basically, we're using nuclear analytic technique, isotope and radio tracer for analyzing plastic impact on live BL water, because this is, of course, also in the mainstream covered by the UN Sustainable Development Goal, and we are focused on 14, but it helps in different ways. So what we know about marine plastic pollution, basically, we can find marine plastic everywhere. This is true for in the atmosphere. We can find it everywhere we saw, because it's not all we used to see all those plastic patch around the ocean, the waste in some area, but basically it's not only what we see, there's also something that we don't see. And this is why research is important. Try to see how does plastic pollution impact our environment. And when we talk about microplastic, this is even more important. And that's why it's in the air, it's in the water, in the food that there's a lot of important route that we are exposed to. And this is not a problem by itself. We can see, well, it's there, it's not a big deal. No, because we have seen that plastic can be toxic. And this is the way it depends on the size, it depends on the exposure, and this need to be, this is more and more known. And of course, since it's everywhere and since it's toxic, many organisms and humans ingest it. And so this is important to understand what is in the future, how, at which degree. So we know it's toxic, but we don't know yet how much. And that's why we're going to the known thing. So it's important. And with the technology that we develop, the nuclear analytical, the tracer, the isotopic techniques, we can assess the source, the importance of the things. We can understand how it goes and how it circulates among the ocean. Now we'll see that in more details. We can gain information on the fates. Again, as I said, we know that it's ingested, but we don't know what is the actual fate of this ingestion to marine environment and even to humans. And basically also we can understand how plastic interact with marine life in general. So it's not only the gain information, but to understand. And this is why nuclear science and techniques can contribute. So for the source, to assessing the transport, I'll go more into detail about the technology that is in place right now. So nuclear isotopic technique can be used to characterize and monitor microplastics. So we have tools that can tell you this is this type of plastic and this is where it's located. This is super important because we have a massive amount, and scientists are saying that more than 8 million tons of plastic released in the ocean. And so that's what we need to know. It's not only, as I said, the large marine debris, but it's the particles. And this is where our techniques is really important. So here, for example, when we talk about global monitoring, we need to know, we need to optimize. And this is where the technology is going. Where is located? Because we have the big patch in the ocean, but then after there's other aspects. So with the tracer technique and the stable isotopic techniques, it could complement just the visible counting of plastic. We can tell us where it's coming from. For example, quantify which is atmospheric and river inputs, so discriminate which source of pollution. We can test some model based on different use of these techniques, and also characterize it. This is important. And in the future, what is also important is with these techniques, I give here some example of techniques. For example, we have FTIR using infrared technology, so FTIR, LDR, but also Raman, which is also a nuclear analytical techniques. We can discriminate and then really define what type of pollution that we're facing. And here is another example of techniques, nuclear technique to assess what is the fate, but more the chronological assessment, which means basically we can see if this is a coral core, a sediment core, we can assess with time, determining the dating of this sediment core. We can define how was the pollution in the different years. So we can see the increase of pollution and try to see if the pollution was the same with the same compounds, or there was a variation with the different type of polymers that we can find in the environment. After that, this is also important. So the monitoring, as I show you in the first part, is super important. Our technology has a role to play for helping to characterizing and to harmonize the technology, the method for monitoring. This is part also of the thing that we were talking with the aspect of transfer of knowledge and harmonization of monitoring to have a global unified methods for determining the plastic pollution in the environment. But basically after, the next step is also to try to use these techniques to see how microplastic, and even now we can go further with nanoplastic, how this is impact marine life. So here in Monaco, we have an history of experiments doing to understand the fate of pollutants on marine organisms, also on other organisms like freshwater organisms, but mainly we focus on marine organisms. And in the context of plastic, we are trying to see with different approach to see, first of all, the plastic, how does it impact any kind, from the phytoplankton to the fish, how the presence of plastic impact organisms. Do they react similarly? Is there a transfer of contaminant? Because as you may know, plastic is also can play a role as a sponges for other chemicals, or they are in even the way they are manufactured could also have some plastifiers. So we are trying to assess how marine life or an organism are impacted by either the plastic as a mechanical part, the chemicals that are related to plastic, also the absorbed contaminants from the fact that they are circulating and they are absorbing some contaminants to the organisms. And this is super important because this is a way where all contribution with nuclear and isotopic technique can be complementary to the existing as ecotoxicological, let's say, the studies looking at the impact of plastic on organisms. So the contaminant was part of the studies in the past, and this is what we use, radio tracer. I don't know if you're familiar with that, but basically we can use a tracer that is radioactive to find out if, for example, a co-contaminant like a pollutant is transferred to the organism. And we have a series of work that have been developed here that now we are going to share more into activity to share our knowledge to the member states working with us. And also in terms of fate, tracking the fate and transfer is not only the way of following some contaminants, it's also how see or the physiology of the organism. And there's a wide range of different techniques that we can use for tracking the fate and the transfer of assessing the stress to organisms. This is going through, again, radio tracing, try to see how they deal with the presence of plastic to get access to the nutrient, for example. We can imagine also this, try to see compared to a control, how they deal, how the health is impacted. And this is a unique technology to fill this gap of knowledge, because right now we have the development of the science is really important, but we need to go further because there's still gap of knowledge. And the next step really in terms of this plastic is basically we will reinforce our activity in our laboratory to be able to respond to the question to member states about the monitoring. As I said, having the up-to-date techniques to help member states to have this harmonized methodology for monitoring microplastic in the environment. Also, we will try to push for leverage of partnership, as mentioned by my colleague Selina, in a wider perspective. This is also true for the study on the downstream, trying to understand with colleagues, because it doesn't work by working by ourselves. This is the partnership is super important for having a wider utilization of these techniques and a wider understanding of the impact of marine plastic and the marine environment. And of course, right now we are ongoing on a process for developing guides and protocols for sampling, quantification, characterization to have this, as I said, harmonized methodology for monitoring plastic. And the transfer of knowledge is key for the agency, and this is what we're working toward. Finally, we are aiming to establish a new plastic monitoring network for exchanging data, knowledge, best practice, and this is part of this global initiative and part of our part related to the monitoring side. Anyway, the important aspect is the technological transfer to member states to contribute to these sustainable development goals, especially what we're saying, life below water, the SDG 14, and also the opportunity for reaching this goal of having a sustainable environment, especially in sustainable marine environment. This is done for my part. I would be happy to respond to any question. And again, thank you for the organizer to inviting us.
Yes, we have received several questions. I hope you can hear me. First question is, how much are technologies for plastic recycling available to countries around the world, being aware that advanced solutions, especially in highly regulated areas as nuclear applications, can be costly, solution might exist, but not to be easily available. In relation to this, can these solutions be provided by the IAEA to member states?
Thank you very much for this interesting question from our part in the area of recycling of polymers. Of course, we are conducting several activities. In fact, we are pleased to share with you that we have a participant also from Serbia in our regional training course and workshop to develop feasibility study on how this technology can improve the recycling of polymer in each country, because this is a very unique technology, but has different approaches. No, of course, depending on the situation of each country, is how we support them. No, but in the generic way, the activity that we had conducted were on the try to improve the knowledge at the researcher and also the project team that are participating in this kind of application, and also supporting with experts in the development of technical feasibility study of, pilot scale plan on a specific application. Because, for example, some countries are considering to convert or to include plastic waste into structural material. Some other are considering the chemical recycling assisted by radiation technology, so are going to produce fuel or feedstock. So it's completely different, the kind of application, and of course, the even equipment of Gamma facility and the size, the shape, the configuration, which are the other integrated system that should be included in this whole system. Sometimes we need some pre-treatment, then the radiation, and the post-treatment to obtain the final product. So it depends on the application, the cost, the economic part. Of course, we are at the R&D step with some inclusion of some private sectors to develop the best and more realistic technical feasibility study. But we are still improving the technology to try to reduce the potential cost that this technology can have, but it relies mainly on the equipment, the e-beam that should be included in this facility. And it depends on the application, which is the e-beam that has to be considered. So it is quite relative, but of course we can extend more information. Everyone that wants to have more information can send me an email, and we can share some also reports and some publications that we already have on board. So thank you for that.
Thank you, Mrs. Horak. I have one more question.
Okay.
It can be... okay.
No, it's just short. So basically, in the agency for the downstream part, for the monitoring, this is much more easier because the technology is already existing, and through the capacity, it's not only through the nuclear application department, but it's more through the technical cooperation. There's already ongoing project and there's probably future project related to that to transfer the technology and to build the capacity in the countries related to that. So that's jointly with our colleague upstream. There's a way and there's facilities to do that. So we are on the way to try to push as much as possible to deliver this kind of knowledge, and also try to build the capacities in the countries, on the member states, including not only on marine. I mentioned marine, but it's also on landlocked countries. So this is the way. There will probably be a European regional project related to this monitoring aspect, and it will also include more aquatic environment. So it's not only marine, but it will be also freshwater. So this is the way forward for us. Thank you.
Thank you, Mr. Metian. The next question is, it can be understood that certain level of pollution is result of lack of knowledge and awareness. Which modalities of raising knowledge and awareness are being implemented in order to provide for better understanding of potential hazards of plastic waste to the environment? Will you or Mrs.
No, I will start. Sorry, Selina. No, definitely, as I mentioned, we know a lot, but there's still a question mark for many aspects, and that's the development technology that we are doing here. We try to push for collaboration with people that working on that right now. So there's more and more study to try to find out what is the fate of this in terms of environment, and basically the awareness is part of also, we did not present that, but the awareness and try to make people know about this, the risk in the future, the importance of recycling, the importance of monitoring, and try is also part of this project, because this is, as mentioned by this question, it's a really important fact that people need to know. And we are scientists is also to be objective. Is there a fate or there's another problem with plastic? And depending, as I said, to the size, to the type of plastic, and so on and so forth. So yeah, this is a big part of the project.
Thank you.
Just to add, yes, it is very important, the point that it was arrived through this question, and also it is very challenging, this topic, no? How to get awareness of the whole society, because it is an integrated approach. So it involves so many stakeholders, no, in each country, not only at the national level, also at the regional level, because sometimes plastic waste go around the world. So we already know about that. So it is very important to get awareness, but we are just part of this technology. No, we are trying to promote and support the awareness through different activity, of course, with policymakers, with the private sector, to get them engaged in this alternative advanced technology. No, this is another advanced technology in the case of recycling of plastic, no, that can provide some solutions. But of course, there are another international group already working on this topic. No, UNEP, United Nations Environmental Program, has a very nice joint working group that are promoting this and also providing this and sharing knowledge through different drafts, to different reports, to the different high-level authority with the ministry. So it's a very challenging topic, but I believe that it can be done, yes, of course.
Thank you, Mrs. Horak and Mr. Metian. It was my pleasure to be your host today. So thank you very much. Hvala predstavnicima Međunarodne agencije za atomsku energiju. Pitanja smo imali i odgovorili, bila su veoma zanimljiva, a treći panel bavit će se likom i delom Nikole Tesle kao jednog od naših najvećih naučnika, i to u delu njegovog rada koji je manje poznat, a tiče se istraživanja u oblasti rentgenskih znaka, o čemu će govoriti poznati strani i domaći stručnjaci koji će prikazati dostignuća Nikole Tesle iz malo drugačijeg ugla. Pozivam profesora Michaela Pravicu sa Univerziteta Nevade u Las Vegasu da nam održi predavanje na ovu temu. Gospodine Pravica, izvolite.
Hello, my name is Michael Pravica. I'm a professor of physics at UNLV, and I've been working on X-ray physics since 2003. And I wanted to discuss Nikola Tesla's contributions to X-ray science. Nikola Tesla taught us how to generate and safely accommodate high voltages and high frequencies. He also taught us about the importance of natural resonance in any physical system and how to harness tuned electrical and magnetic fields to stimulate and detect resonances. And he also taught us how to transmit and receive electrical energy wirelessly. So first of all, just to give a perspective of where we're at when we're discussing Nikola Tesla's contributions and his involvement, we need to understand this is mostly starts in the 19th century. So in 1886, Heinrich Hertz discovers electromagnetic waves, verifying Maxwell's equations. In 1891, the Tesla coil is invented. In 1894, Tesla starts studying X-rays after observing photographic plate damage from some sort of an unknown invisible radiation. In 1895, sadly, Tesla's laboratory burns down in a fire of mysterious origins. 1895, Wilhelm Röntgen is credited with discovering X-rays. 1896, Tesla publishes some of the first X-ray images. In 1897, J.J. Thomson discovers the electron using a cathode ray tube. 1900, Planck's discovery of quantized energy occurs, which is really considered the dawn of quantum mechanics. 1905, Einstein proposes the concept of the photon, a quantized bundle of electromagnetic energy. 1911, Rutherford, Marsden, and Geiger, those are two students of Rutherford, graduate students, discover the dense atomic nucleus. And finally, 1913, Moseley discovers the relationship between X-ray energy and atomic number. So as I give my talk, I would like you to put this in perspective, that at this time was an exciting time in physics and for humanity in general, but at the same time, nobody really understood what was really going on. So Tesla was part of that. He had tremendous insights. Some of them were not quite correct. Many of them were correct. And so I would just, at least when we consider his contributions, we need to put in perspective where he was, where was humanity from the standpoint of X-ray science. So to start off, as I mentioned, in 1891, Tesla invents the Tesla coil. This was one of the first achievements to create high voltage and high frequency safely that wouldn't kill people. And the amazing aspect of the Tesla coil is you can go from volts up to megavolts very easily with voltage amplification via tuned LC circuits. So just to give a perspective, what are X-rays? Because again, at that time, nobody understood what X-rays were. They're electromagnetic in origin. They travel with the speed of light. They have no mass, but yet, due to the wave-particle duality, they are both waves and particles. They're highly penetrating. They can pass through glass at the right energies. They're also highly ionizing, and therefore they can also damage matter. For example, your skin. They are more highly absorbed by higher Z or higher atomic number elements. For example, X-rays will be more easily absorbed in lead than aluminum. And they're in a certain energy range, about 100 electron volts, that's a unit of energy, to 100 kilo electron volts are the typical types of energy ranges. And I'm going to come back to this. Hard X-rays are a little higher energy, so they're greater than 7 kilo electron volts. Soft X-rays are softer, so they're less energy, so they're less than 7 kilo electron volts. I should also just mention hard X-rays easily penetrate through air, centimeters of air or more, depending on their energy. Soft X-rays are very easily attenuated and stopped in air. So basically, what we're talking about for much of, if we're talking about X-ray technologies, we're really interested in the hard X-rays. And then just to give you a perspective, the wavelengths or the order of X-rays or the order of bond lengths in molecules or atomic dimensions, which are typically of the order of angstroms, 10 to the minus 10 meters. And just to give you an understanding, better perspective, 25 kilo electron volts is about 0.4 angstroms. So that's a very nice energy for X-ray spectroscopists and people doing X-ray diffraction. And so from Tesla's time, if you see on the left, the scale of electromagnetic radiation, you can see that Tesla was involved in radio, and then microwaves, visible, even visible, because his Tesla coils could produce visible light, obviously. But not much was known at that time because we didn't have the means to detect ultraviolet, which is higher energy. We're looking at maybe greater than 5 EVs, and then transitioning to X-rays, and then, of course, gamma rays, which go on to as high as you want to go, MeVs and beyond, GeVs, giga-electron volts, tera-electron volts. Those are all in the regime of gamma rays. So Tesla was one of the first people ever to take an X-ray radiograph, or basically use photographic film and shine an object. For example, on the right, you can see his hand, and basically realized that the X-rays were very penetrating. They would go through the skin, which is a low atomic number. That's organic materials, carbon, hydrogen, nitrogen. And then they would be absorbed by the bones, which have a lot of calcium in them, which is a higher atomic number. On the left, you can see Röntgen's, one of his early radiographs or X-ray pictures taken of his wife's hand. And you can see it's much poorer resolution, more faint. And in fact, in the center, you can see a letter that when Tesla sent him some of these images that he had taken, Röntgen was totally impressed and said, "Boy, I wish I knew how to do what you've done," because Tesla had figured out very quickly how to use the X-rays to take pictures. And in fact, he was so good at it that he, on the lower left of this website, you can see that he was actually write Röntgen and take it, probably in some sort of metallic paint, and then take an X-ray radiograph of that. That's how good he became at taking at X-rays. And at the time, his discoveries were actually widely popularized, discussed in the American mainstream media. So again, there's so much we could go into. I just don't really have the time for a 25-minute talk. But the point is, I just wanted to emphasize a few quotes of Tesla's that show basically where he was at, his commanding understanding of X-ray science. So this was in the Scientific American. It was an article about him, says experiments conducted by Nikola Tesla with voltages of 2 million volts have convinced him that 100 million volts could be produced, and it might be possible to break down the atomic structure of any element and thus liberate a certain amount of energy. What he was really talking about was X-ray induced fission or fusion, and so basically high energy physics. And he said, but he was a little skeptical. He said, even if the feat could be accomplished and sufficient energy would be set free, he's thinking from E equals mc squared, Einstein's famous equation, that the relationship between matter and energy, there still remains the enormously difficult problem of devising a means of utilizing the energy in a practical way. Well, he's talking about basically thermonuclear fusion. To this day, that's a big challenge that we're working on, trying to understand you can produce, there's hydrogen bombs. You can release all sorts of energy with fusion. The question is to contain it. So Tesla also made great improvements in the cathode ray tubes that could generate X-rays. Bear in mind, as we said, soft X-rays are kind of useless in the air. They get very easily attenuated. On the upper left, you can see a Crookes tube. That was one of the early devices that Röntgen had used to discover X-rays. But the problem is you have the cathode and you have the anode. And so the idea is that you've got the electrons going from the cathode, smashing into the electrode in a DC kind of a way. And then they make these shadows. Again, this cathode tube is evacuated. So it's a vacuum, okay? So that reduces the scattering and the collisions of the electrons. This is, of course, was not understood back then, but it's understood today. And so the idea is that the scattering would reduce your signal and then you wouldn't see anything. But what Tesla did in the lower left corner is actually develop a unipolar electrode, so that basically the cathode that was emitting electrons, and then it would smash into the glass on the bottom of the lower left corner. The electrode, you can see little C in the top there. is the wire that connects the high voltage, and then goes to E, which is your electrode, dumps in this evacuated glass, dumps X-rays, and then hits the glass at the end, and then due to something called Bremsstrahlung, breaking radiation, produces copious amounts of X-rays. So Röntgen did kind of resolve that, but Tesla amplified that. Tesla verified all of these things, was one of the first people to actually understand that there's no matter getting outside of the glass. It's pure energy, and those were X-rays. And Tesla, although he didn't publish, he did work on many afterwards. He worked on many improvements to the X-ray tubes, to basically, which made them later became adopted into, for example, Moseley's experiments, and then of course X-ray science in general, medical imaging. And on the right, you can see one of his inventions, where he used an improved tube with the double focus. And he was one of the first people to recognize that X-rays are damaging. They're ionizing, they damage matter. He didn't say it ionizing, he didn't understand, but he said it was damaging matter. And so he figured out ways to reduce the dose for humans. And that was very important for radiography to become, in medicine. And one other last quote is, he said, it was he said, he was quoted in the New York Herald Tribune in 1929 saying, up to 1896, I did not succeed in obtaining positive experimental proof of such a medium. People were confused about this as far as a medium for electromagnetic radiation, or was it matter, etc. But in that year, I brought out a new form of a vacuum tube capable of charging to any desired potential. And guess what the desired potentials were charged with? Tesla coils. So the point is that Tesla was one of the first people to get to really high voltage to generate X-rays necessary to go beyond a glass Crookes tube and actually be used as, for example, for photographs. So he says, operated with effective pressures, he means voltage, of about 4 million volts. 4 million volts, imagine, 1896. 4 megavolts. This is something that was just so beyond anything that humanity could ever do at that time. I produced cathodic and other rays. Again, he didn't understand it. He didn't call them electrons, but these were the electrons, rays of transcending intensity. Sure, higher voltages give you higher flux. The effects, according to my view, were due to minute particles of matter carrying enormous electrical charges. Basically, this is the electron, which, for want of a better name, I designated as matter not further decomposable. These are electrons. And at first, J.J. Thomson, who was considered the discoverer of the electron, didn't believe this, that this idea of these kind of quantized packages of little bullets, if you will, of matter. And that was Nikola Tesla. Okay. So again, just very briefly, some of the areas of modern physics that Tesla significantly impacted. Again, this is not, the talk is more on X-ray physics, but you can see his imprint in much of modern physics to this day. And one other thing to just talk about is that not only was Tesla a master of taking X-ray photographs, a master of creating X-ray tubes, he actually understood the concept as distributed resonance. And the idea of that distributed resonance ended up becoming very popular and useful for high energy physics to generate the megavolts to accelerate particles. And so I'm actually a high energy physicist. I mean, I work with X-rays produced by synchrotrons. And so you can see here, this is by Nobel laureate David Sloan, one of his first publications on the subject of radio frequency generators. He mentions using a Tesla coil to basically boost up the voltage into these megavolt ranges for acceleration of high energy particles. So why is this an issue? Because today we use Tesla's concepts of distributed resonance to accelerate particles, including at the Advanced Photon Source, which is the United States' brightest X-ray source, and also the Canadian Light Source, where I do a lot of my experiments at both places. And you can see in the Advanced Photon Source, there's a ring, and the ring accelerates particles, such as electrons, to very high energies, giga electron volts, and very near the speed of light. And then what they do is they wiggle or use these radio frequency quadrupole accelerators to basically accelerate them, just like you're accelerating a roller coaster. And so you're accelerating bunches of particles, and then basically that's what allows us to, then we wiggle them at strategic locations to produce copious amounts of X-rays by Einstein's principle of the acceleration of electromagnetic charges. So just in a very brief, I've been using Tesla's ideas for something I call useful hard X-ray photochemistry, where I use hard X-rays greater than 7 keVs to actually break up compounds, molecules, strategically to release reactants, and then I can use those reactants to produce other materials. And whereas X-rays have been seen as something, damaging, that you have to be careful of what you're doing, I actually take the bull by the horns and I say, let's celebrate that damage and let's drive new channels of chemical synthesis. And so one of the materials we made, is a new, it's a wide bandgap semiconductor. We call it doped polymeric carbon monoxide, or doped poly-CO. And here you see we use the X-rays greater than 16 keVs. This is to ionize a K edge in the strontium and then break it up, the oxalate group, and then the oxalate breaks down into carbon monoxide, and under a very slight pressure, it polymerizes. And you can see here, you can see here a damaged track going right through a sample confined between two diamonds for high pressure, and going from top to bottom in the lower right, with the middle right photograph, using X-rays. And we've actually made a new material. We have a patent granted on it. We're hoping it'll be useful perhaps for solar applications or sensors for extreme conditions. We've also, using X-rays, we've synthesized a new structure of cesium superoxide. So again, X-rays are highly ionizing, so we are overcoming any chemical activation barriers and enabling novel routes of chemical synthesis in the thermodynamic phase space. And here's one perfect example where we've created a new structure, never been reported before. And as you can see on the lower right, it's a little complicated, but it all starts out with X-rays, producing photoelectrons and then enabling novel routes of chemical synthesis. So takeaway messages: Tesla used his coils to easily generate the necessary voltage to create X-rays, at least according to his reports, up to 18 mega electron volts. Thus, penetrating hard X-ray radiation greater than 7 keVs could easily be produced, which makes X-ray science essentially practical. He understood the notion that X-rays are high-velocity bullets or quantized. He didn't use the word quantized, but basically that's what he was saying. He described X-rays as small mass, high charge, and convinced J.J. Thomson of this. He recognized that X-rays are created by the interaction of cathode rays with matter. He was one of the first scientists to report the dangers of X-rays and develop methods to reduce X-ray exposure, shielding, distance, flux reduction. We all use these techniques to this very day. He tried to use X-ray optical methods, for example, lensing, during his radiographics efforts. He wasn't successful, but you can see what he was thinking. He was thinking ray tracing, treating X-rays just like we treat visible light. And he was right. It's just you need to, they're higher energy, you deal with different techniques, okay? You have to adopt the techniques. He didn't know that because it was the late 19th century. He was one of the first scientists to realize the importance of X-ray photographs to see into the body for medical purposes. That's used to this very day. That's a standard field of medicine, of science. And then let me emphasize this. Using his Tesla coil, he was likely the first human being ever to produce X-rays because he figured out how to get into the tens of kiloelectron volt range and beyond. There's no question he produced the X-rays. Did he understand what he was producing? No. But again, that took a concerted effort of many scientists, not just Röntgen, others, Becquerel, Marie Curie, etc. It was an exciting time for science. But in my opinion, there's no question Tesla was one of the forefathers of X-ray science. I would like to acknowledge Serbanum conference organizers for inviting me to present this remote lecture. I would like to thank Robert Misch, who I convinced got him excited about Nikola Tesla, and he created all these wonderful coins, including one that are being minted in Serbia, including one that discusses Tesla, shows Tesla's radiograph of his hand. I would also like to thank the Serbian Royal Society of Arts and Sciences for inducting me as a foreign member and granting me their Tesla Medal for efforts to tell the world about one of the greatest geniuses. Thank you very much.
Hvala gospodinu Pravici. Sada pozivam gospodina Branimira Jovanovića, pomoćnika direktora Muzeja Nikole Tesle u Beogradu, da nam se obrati. Gospodine Jovanović, izvolite.
Dobar dan i pozdrav svim učesnicima konferencije o nuklearnoj sigurnosti. Tema o kojoj ću ja govoriti danas nije mnogo eksploatisana kada je u pitanju Teslino delo. Uglavnom je bila namenjena stručnjacima i ljudima koji su usko u jednoj oblasti elektrotehnike ili eventualno tehničke medicine, a to je Teslino istraživanje X zraka. Da bismo razumeli zbog čega je došlo u stvari do toga, jer to istraživanje Teslino nije ni malo slučajno nastalo, koji su bili uzroci, koje posljedice, a neophodno da se malo prisetimo i nekih detalja vezanih za Teslin rad. I evo ja ću uključiti sad prezentaciju, možemo da krenemo. Do takvog istraživanja u stvari ne bi nikada ni došlo da Tesla nije napravio svoje čuveno otkrića u oblasti polifaznih struja, da nije zapravo kao mlad 26-godišnjak u Budimpeštanskom parku otkrio na koji način obratno magnetno polje može da se stvara na izmeničnim strujama, što se u to vreme smatralo za praktično nemoguće. I ovde sa vaše leve strane vidite taj čuveni Teslin patent koji je dodušao tek 6 godina kasnije uspeo da patentira u Americi. To je, njemu je objasnio način stvaranja obratno magnetnog polja na izmeničnim strujama. I iz tog patenta proizašlo je još 35 novih patenata, znači ukupno 36 patenata čine taj Teslin čuveni polifazni sistem, koji je prvi koji je shvatio važnost tog sistema za tehnologiju i budućnost Amerike pa i celog sveta, bio je čuveni inženjer, pronalazač američki George Westinghouse, koji je te patente jedan po jedan polako kupio, dok nije kupio celu grupu, i počeo je na osnovu tih patenata da proizvodi motore, generatore, koje vidite sve ovde na desnoj strani vašeg ekrana. Konačan trijumf, ceo taj Teslin sistem polifazni doživeo na Nijagarinim vodopadima, bilo je potrebno još otprilike 8 godina i 1895. je bila puštena prva struja u rad, a ceo sistem je zaokružen 1896. godine i ovde vidite na sredini ovu čuvenu ploču, nazivnu ploču koja stoji dan danas na Nijagarinim vodopadima. Kopija te ploče je u našem muzeju ovde u Beogradu i tu u stvari piše, ovde sitnim slovima, ne vidi se, ali od 13 patenata koji su učinili taj polifazni sistem, 9 je bilo Teslinih, 2 patenta su pripadali Schmidtu, 1 Kennedyu i 1 Stanleyu. Ovde sa leve strane jedna grupa poslovnih ljudi je slikala se na Nijagarinim vodopadima, ali ovaj čovek ovde, to je John Pierpont Morgan, to je čuveni bankar i čovek koji će kasnije veoma važnu ulogu igrati u Teslinom životu i u njegovim istraživanjima, pokušao da ostvari bežični prenos struje, nešto što je još više nadilazilo ovaj projekat vezan na njega. Sad, kako je došlo do istraživanja X zraka i na koji način je Tesla uopšte u tu oblast ušao? Još krajem 1878. godine Tesla je posle nekog vremena koje je proveo u Westinghouse-ovim fabrikama pomažući da se razvije njegov sistem polifaznih struja i da se usavrši konstrukcija njegovih motora, njegovih generatora, čuo za eksperimente čuvenog Heinricha Herca, nemačkog mladog istraživača, koji je u stvari dokazao teorijsku postavku Maxwellu da elektromagnetni talasi postoje. I evo ovde, vratit ću se na ovaj slajd, ali evo ovde sa vaše leve strane zapravo vidite taj eksperiment koji je izveo Heinrich Hertz. Tu je taj Ruhmkorffov induktor, uređaj koji mogu da stvara struje visokog napona, i ovde je jedno otvoreno praktično antensko kolo, dolazilo je do varničenja, stvarali su te elektromagnetni talasi koje je Hertz detektovao ovim prstenastim prijemnikom. Taj članak i taj ogled Hertza izazvao veliko uzbuđenje u svetu i mnogi naučnici su krenuli tim putem. Pažnju je privukao i Tesla kao jedan vrstan pronalazač koji je imao fantastičnu intuiciju, video je tu jednu veliku mogućnost da razvije eksperimente i da otvori jedno potpuno novo istraživačko polje. Šta je bio problem kod Hertzovih eksperimenata? Pa ovaj uređaj je bio vrlo primitivan i vrlo nesavršen i stvarao takozvane impulsne, visokofrekventne struje, prigušene oscilacije su bile u pitanju i Tesla je shvatio da mora prvo da napravi jedan, tako da kažem, daleko savršeniji uređaj. U stvari on je razmišljajući kako bi usmerio ta svoje istraživanje stroje visokih frekvencija, odredio četiri neka pravca u kome će ići. Prvo da razvije, usavrši uređaje za proizvodnju visokofrekventnih struja, a zatim bio je svestan da će to, kao što svako rešenje problema izaziva i stvara nove probleme, tako će i taj razvoj tih uređaja stvoriti potpuno nove probleme na nivou tehnike i tehnologije i morat će da stvori prateće tehnologije i da ih usavrši, a onda da se posveti eksperimentima da celo to polje što je moguće više temeljno istraži i da ispita mogućnost, tako da kažem, kako fundamentalno, tako i primenljivih rešenja koji su u toj oblasti krivi. I vraća se ponovo na ovaj slajd, ovde sa desne strane nalazi se Teslin čuveni patent Teslinog električnog oscilatora ili kraće rečeno Teslinog transformatora, na engleskom se to još kraće kaže Tesla coil ili Tesla namotaj. To je u stvari uređaj koji je bio u stanju da proizvodi visokofrekventne i visokonaponske struje sa neprigušenim oscilacijama u najširem mogućem spektru. Pre Tesle naponi do koji se išlo bili su negde do 5000 volti, ali posle Tesle sa tim naponima išao čak do više miliona volti. U Colorado Springsu imao je taj oscilatorni transformator posebne konstrukcije koji je dosizao napon od 12 miliona volti, a na Long Islandu planirao još jedan mnogo oscilator sa još višim naponima. Ovde možete da vidite na ovoj slici Teslinu laboratoriju, ali pre toga možda da vam kažem da je Tesla radeći sa tim strujama visoke frekvencije, visokog napona, zapravo došao do nekoliko fundamentalnih otkrića koji su dalje odredile čitave oblasti u kojima je on istraživao mogućnost primjene tih struja. Znači Tesla kroz tu tehnologiju prošao kao, kako bih vam rekao, kao kroz jednu nepoznatu zgradu u kojoj se nalazila prostorije sa zaključanim vratima u kojima niko nije znao šta se krije. On je potvarao ta vrata, upalio svetlo u tim prostorijama i onda produžio dalje u pravcu koga je njega zanimalo, a mnogi koji su išli njegovim putem u te prostore su onda ušli i počeli da eksploatišu to što je on ne samo nagovestio, nego i pokazao. Dakle, jedno od prvih njegovih fundamentalnih otkrića bilo je da struje visoke frekvencije i visokog napona pod određenim uslovima mogu da deluju na vlaknu ili elektrodu u sijalici i da izrače jednu znatno veću količinu svetlosti nego što je to bilo u stanju takozvana sijalica sa užarenim vlaknom, koja je već bila poznata, kao što znate, to je čuveni američki pronalazač Edison u to vreme već patentirao i ta se sijalica eksploatisala, a isto tako je već davno bila u upotrebi takozvana lučna lampa. Iz tog Teslinog istraživanja upotrebe struje visoke frekvencije i napona u osvetljenju izašao je taj pronalazak tog hladnog svetla, ali isto tako je izašao i rad na X zracima na koje ću se malo kasnije vratiti. Onda je Tesla utvrdio da se u njegovim oscilatorima dešavaju nekakve elektrohemijski procesi koji mogu da budu upotrebljeni za izdvajanje određenih jedinjenja u vazduhu. Konkretno, on se usmerio na izdvajanje azota iz atmosferskog vazduha koji ima jako mnogo i nagovestio upotrebu tog izdvojenog azota za proizvodnju veštačkog đubriva, za proizvodnju ozona i možda nekih drugih proizvoda. Nemojmo zaboraviti da pričamo o poslednjoj deceniji 19. veka, kada se sve to dešavalo i kada ove industrije još nisu bile ni u začetku. Dalje Tesla otkrio da njegove visokofrekventne struje imaju povoljno fiziološko dejstvo na ljudski organizam, da prolaze kroz, bez obzira na visok napon, da prolaze kroz površinu ljudskog tela i da imaju određena stimulativna dejstva i odatle su potekla njegove istraživanje u medicini, koji je nasledio i čuveni francuski fizičar Darson-Valle, pa danas imamo takozvane Darson-Vallizacije, stare metode koje su po tom naučniku, to je još jedna mala nepravda koja je, tako da kažem, Tesli učinjena, znači ne govorimo o teslinizaciji, nego Darson-Vallizaciji, ali eto, takva je priroda tih pionira i istraživača koji su otvarali te nove oblasti. I najzad, ono što je za Teslu možda je najbitnije bilo, to je upotreba struje visokih frekvencija i visokog napona za prenos signala i za bežični prenos energije i na to ću se malo kasnije vratiti. Dakle, ovde na ovoj fotografiji sa leve strane ta Tesla laboratorija i ovde možete da vidite različite konstrukcije Teslinih oscilativnih transformatora, spiralni, cilindrični, ovde su razni oscilatori za terapeutske i druge svrhe, a ovde imate dve fotografije, ovo je Teslin lik sa njegovim vakumskim svetlom i ovde Tesla u ruci drži jednu od naučnih knjiga, osvetljena njegovim svetlom koji on proizveo svojim sjelicama. Isto tako, na ovom slajdu možete da vidite kako je Tesla razvijao svoj sistem 4 kola u rezonanci i najzad patent tog sistema koji predstavlja osnove savremene radiotehnike, da Tesla je prvi pokazao da antena, izdignuta antena sa kapacitivnošću na kraju, uzemljena, kada se uspostave rezonantni uslovi na predaju i na prijemi, na predaji i na prijemu, stvara jedan sistem kojim je moguće prenositi signale na to je opet, tu oblast je najviše razvio kasnije italijanski fizičar Marconi, Tesla je tu doživao velike razočaranje što su drugi tvrdili da su pre njega to pronašli, tako da, ali to je sad predmet jedne druge priče. Da se vratimo konačno na temu koja je predmet ovog predavanja, to je rana Teslina migracija. Znači, još na predavanju pred Kraljevskim društvom u Londonu 1892. godine Tesla je, prikazujući svoja prva iskustva u radu sa svojim oscilatornim transformatorima, primetio da njegovi oscilatori emituju, kako se on izrazio, obične vidljive i dve vrste nevidljivih talasa, a to je, kako je on rekao, to su obični tamni talasi svih talasnih dužina, i zajedno sa njima nepoznati talasi tačno definisanog karaktera. Međutim, do temeljnijeg ispitivanja ove pojave došlo je krajem 1894. godine kada je vršio eksperimente sa fosforescentnim i fluorescentnim telima i njihovoj upotrebi u osvetljenju. Međutim, evo ovde sa desne strane vidite neki samo deo Teslinih cevi specijalno konstruisanih, imao je stotine bukvalno tih konstrukcija koje je razrađivao i pripremao za patente. On je krenuo u stvari sa eksperimentima sa takozvanom Crooksovom cevi i ispitivao je pojave koje se tu dešavale i različite efekte i primetio je da postoji jedan uticaj rada tih cevi na fotografske ploče koje su bile postavljene u laboratoriji. Taman se pripremao da tu pojavu intenzivnije, tako da kažem, ispita upotrebom Lenardovih cevi, a onda je došlo do požara, poznatog požara u njegovoj laboratoriji 13. marta 1895. godine, kad je njegov rad bio zaustavljen na neodređeno vreme. Tesla je bio u jednom zaista onako jednoj strašnoj situaciji, možda je malo poznato da je između ostalog rekao da je u tom požaru izgoreo rukopis knjige koju on pripremio, koja se zvala Bajka o 1001 indukcionom motoru. U toj knjizi objavio je 1001 konstrukciju indukcionog motora i ta knjiga koja je trebala da bude objavljena je izgorela, a naravno Tesla više nikad nije palo na pamet da uđe u taj napor da ponovo rekonstruiše celu tu knjigu, jer se bavio nekim drugim stvarima i smatrao je da mu je vreme veoma dragoceno. Takođe u tom požaru izgorele su stotine cevi koje on, specijalno konstruisani cevi koje on pripremao za različite istraživanja. Na jesen iste godine Tesla je uspeo da obnovi svoju laboratoriju i da se preseli u ulicu Houston, a međutim nije znao da je već u to vreme u novembru nemački fizičar Rentgen ispitivao, istraživao uticaj tih specijalnih zraka koji su po njemu kasnije dobili naziv rentgenski zraci i već 8. januara 1986. godine objavio je svoje otkriće naučnom svetu i na taj način praktično pretekao Teslu. Tesla je, čim je saznao za ovo, obnovio svoje eksperimente sa svojim specijalnim i sa svojim oscilatornim transformatorima i ovde na ovoj slici vidite dva radiografa koje Tesla proizveo. Na desnoj strani je rame nepoznatog čoveka, vidite ovde prelom ključne kosti, a ova glava verovatno pripada Tesli sudeći po nekakvim detaljima koji su karakteristični za njegovu fizionomiju. I Tesla je ta svoja otkrića počeo da objavljuje u časopisima, stručnim časopisima tog vremena, pre svega u časopisu Electrical Review. Objavljivo je cele 1896. godine svoje otkrića i pokazivao zapravo rezultate do kojih je došao. Ono što saznajemo iz tih svih članaka, a onda iz predavanje koje je održao 1897. godine o X-zracima u Njujorškoj akademiji nauka, da je prvi otkrio takozvane reflektovane X-zrake, da je konstruisao cev za emitovanje X-zraka sa mogućnošću automatskog podešavanja potpredska u cevi, da je zapazio štetno delovanje X-zraka na čoveka, da je prvi dao i predložio metalni zakon za zaštitu lekara od X-zraka i da je eksperimentalno dokazao da svako intenzivno zračenje u prirodi proizvodi X-zrake. To su bili ti nekakvi osnovni Teslini doprinosi ovoj oblasti i verovatno bi ovde možda priča o X-zracima bila i gotova da ne govorimo o Tesli, o čoveku koji je celog svog života kumulativno radio i koji je, tako da kažem, se vrlo često tako da kažem, kombinovao svoje otkriće u različitim oblastima i kasnije u svom životu se vraćao na njih. Tesla je napustio 897. godine tu oblast zato što je njegovu pažnju sve više privlačila prenos signala bežičnim putem, ali isto tako i mogućnost bežičnog prenosa energije i kakve to veze ima opet sa X-zracima, pokušat ću sada da objasnim u nekoliko narednih slajda. U svakom slučaju Tesla otišao u Colorado Springs 1899. godine da bi proširio mogućnost, da je povećao napone koje, znači u svojoj laboratoriji u ulici Houston mogu da proizvede do 4 miliona volti, a onda je to postajalo već opasno i u Colorado je napravio specijalnu laboratoriju i u toj laboratoriji imao je specijalno konstruisan transformator sa takozvanim dodatnim kalemom na kojima je ispitivao mogućnost upotrebe visokofrekventnih struja i izuzetno visokog napona, pre svega za prenos signala i prenos energije. 4. jula 1896. godine, to je po mom mišljenju možda i najdragoceniji dokument koji se nalazi u arhivi muzeja Nikole Tesle. On je napravio jedan zapis u kome je objasnio jedno svoje dramatično otkriće, a to je da planeta Zemlja ima svoje rezonantne frekvencije i da je on te frekvencije zapravo otkrio u jednom eksperimentu koji se slučajno dogodio na prethodne noći, kada je jedna oluja prešla iznad Colorado Springsa i kada je on detektovao jednim specijalnim uređajem posebne talase koji su se ritmično ponavljali cele te noći u negde vremenskom razmaku od 1 sata. On je rekao da nema sumnje da se radi o postojećim talasima i da konačno ima jedan mehanizam kojim bi mogao celu zemljinu kuglu da, tako da kažem, iskoristi kao jedan savršeni provodnik za prenos energije. I Tesla se vratio u New York i tada je objavio delimično svoj plan. Ovdje je jedna mehanička analogija koja pokazuje zapravo na koji način, tako da kažem, energija može da se koristi, da se prenosi na velike daljine koristeći električni potencijal Zemlje. Dakle, Tesla je rekao da u samoj planeti Zemlji taj elektricitet u jednom haotičnom stanju, ali da postoji mogućnost da se taj elektricitet natera, da on pređe u jedno dinamičko stanje koje je moglo onda dalje da se iskoristi i dao jednu analogiju sa jednom loptom sa elastičnim zidovima koja je puna vode. Znači, kaže, kada počnete ritmično da radite, ako znate dimenzije lopte i ako znate osobine elastičnih zidova, onda ako podesite ritmični rad ovog klipa tako da kad se napravi prvi talas, sačeka se njegov povratak, a onda se napravi u tom ritmu sledeći talas. Dakle, to rezonantno delovanje klipa napravit će specijalne talase unutar kojih i na određenim tačkama možemo da registrujemo određene otklone, odnosno da na određenim tačkama možemo da konstatujemo da postoje mesta na kojima energija može da se, tako da kažem, crpi. Drugim rečima, ako bi na ovim mestima postavili slične pumpe ovoj pumpi, ona bi počela da rade u ritmu kojom radi Dakle, samo još jednom da ovde kažem nešto, posto često postoji zabuna i zloupotreba ove Tesline ideje. Ovde se ne radi ni o kakvoj proizvodnji energije, nego se radi o prenosu energije sa mesta na planeti na koje te energije ima dovoljno do nekakvih drugih mesta na planeti na kojima je do te energije teže doći. Dakle, u pitanju je prenos, bežični prenos energije, a ne proizvodnja energije. Tesla je vrlo brzo zainteresuje onog čoveka koga sam pokazao u jednom od prethodnih slajdova, Johna Pierponta Morgana, koji mu dao novac koji nije bio tako veliki, ali Tesla je mislio, verovao da će on biti dovoljan da on završi taj svoj projekat i on je napravio tu svoju čuvenu antenu za bežični prenos signala energije na Long Islandu i laboratoriju, opremio donekad s tim uređajima, ali samo anteniju nije uspio da završi jer je došlo do poremećaja na berzi, vrednost novca je pala i Tesla više nije bio u stanju, trebalo mu još novca, ali Morgan nije hteo više da daje, jer nije ni obećao da će davati više. Tesla je za Morgana rekao da je bio jedan izuzetno veliki karakter i on se njemu u svakom slučaju divio i bio mu zahvalan na pomoći, nikada ga nije krivio za, tako da kažem, neuspeh svog projekta, ali tu je bio jedan sticaj okolnosti. Osim toga, Marconi je objavio u tom trenutku umeđu vremenu da je preneo signale sa obala Amerike do obala Evrope, transatlantski prenos izvršen, bežičnih signala i to je izazvalo veliku pažnju i Teslin skupi i komplikovani projekat odjednom je dobio jeftinu alternativu. Tesla je pao u jednu vrstu senke i trebalo mu je dosta dugo da se svega toga oporavi, ali nekako u to vreme u senci svih ovih događaja je prošao jedan Teslin patent koji sad nas ponovo vraća na tako da kažem Teslinih istraživanja, na Teslina istraživanja vakumskih cevi i X zraka. Dakle, patent je objavljen 1901. godine, a govorio je o korišćenju takozvane radijantne energije. Šta je u stvari, u čemu se ovde radi? Ovde vidimo da je Tesla pokazao jedan uređaj koji može da prihvati izračenu energiju iz jedne od njegovih električnih cevi i zatim da tu energiju pretvori u nekakve korisne impulse za nekakva pokretanja, a onda je isto tako rekao da u prirodi postoje takva radijantna zračenja, da postoje takve radijantne energije koje neprestano, tako da kažem, su oko nas i da je moguće takve energije koristiti u nekakve praktične svrhe i ovde prikazuje da šematski uređaj sa, tako da kažem, jednim nazovi motorom, jednim krugom koji se pokreće, jednim diskom koji pokreću, tako da kažem, električni impulsi koji se prihvataju ovim antenom i pretvaraju nekakve korisne električne signale. To su naravno jako male energije, ali o čemu se zapravo radi? Kakva je to radijantna energija? Znači šta je to o čemu je Tesla pričao? Samo da se podsjetimo da krajem 19. veka zapravo se gotovo ništa nije znalo o atomu. Znalo se da on postoji i čuveni naučnik J.J. Thomson je 897. godine dokazao da postoji elektron, da postoji to elementarno neelektrisanje, ali o samom sastavu atoma u to vreme se nije znalo ništa i u to vreme, još 1897. godine, Tesla je tvrdio da postoje čestice, po znacima navoda, beskonačne male veličine, odnosno veoma male, mnogo manje od elektrona, da nose pozitivno elektrisanje koje je samo delić elementarnog elektrisanja, da prodiru kroz supstancu skoro bez interakcija i da mogu da postignu brzinu koja je čak i veća od brzine svetlosti, ali je ova brzina ograničena odnosno masivno elektrisanje čestica. Da su te čestice zapravo uzrok radioaktivnosti jer bombarduju i destabilizuju jezgru atoma, da stižu na zemlju iz svih pravaca, da se emituju od svih zvezda, dakle od sunca, i da zbog toga ova radijacija je tokom dana nešto veća nego noću, a da se mali deo ovog zračenja apsorbuje nebeska tela, što izaziva minimalno, ali konstantno povećanje zapremine tih tela i da se ta zračenja, te radijantne energije mogu dokazati eksperimentima sa vakumskim cenom. Dakle, Tesla opisivao zapravo kosmičke zrake i kad je 1913. godine, kad je pokazano na eksperimenti sa balonima da oni zaista postoje, Tesla u to vreme opet daleko bio ispred svog vremena, ali slavu su mu preoteli i u tom smislu neki drugi koji su za to dobili Nobelove nagrade. Međutim, to nije toliko bitno koliko je bitno da je Tesla da se na celu ovu ideju javio negde pred kraj svoga života 930. godina, kada već nije imao više laboratoriju i kada je izašao sa mnogim neverovatnim idejama koje zapravo naučna zajednica nije mogla da razume, niti da komentariše, a više nije ni htela, a s druge strane takozvana žuta štampa u Americi se nasleđivala ovakvim idejama. Zašto je Tesla, tako da kažem, izabrao da ova svoja otkrića, uvide i te svoje poglede naučne na potpuno nove oblasti objavljuju u dnevnoj štampi, a ne u naučnoj? On je zapravo već krajem 19. veka prestao da komunicira sa naučnom zajednicom, kada je toliko daleko otišao sa svojim eksperimentima ispred svojih kolega naučnika koji se bavili sličnim oblastima, da on jednostavno nije imao sagovornika, već samo kočničare. Tada je napustio objavljivanje u naučnim časopisima i bavio se isključivo, tako da kažem, primenjenim istraživanjima, ali onda ga je nepravda koja se desila sa navodnim Markonijevim otkrićima mogućnosti prenosa signala koje su zapravo bila njegova otkrića i, tako da kažem, prečutkivanje njegovog imena u mnogim oblastima koje se bavili drugi naučnici i promoteri, a koje on zapravo otkrio i otvorio. Tesla je počeo da objavljuje ta svoja otkrića i svoja zapažanja nekih 20. i 30. godina u dnevnoj štampi i posebno je tako otkriće nadljivao za vreme proslave svojih rođendana koje je imao običaj da obeleži zajedno sa novinarima 10. jula. Svakog 10. jula. U takvim najavama Tesla je objavio da postoji da postoje energija svuda oko nas, da je on ne samo na tragu, nego da je otkrio načine na kad takvu energiju možemo da iskoristimo, da su u pitanju motori koji će moći da rade praktično beskonačno i da je nama samo da se zakačimo na to što je on zvao zamajcem prirode, will work of the nature. To je ta ideja koja je zapravo uzbudila maštu mnogih, tako da kažem, alternativaca i tragača za takozvanom slobodnom energijom, koji danas govore neverovatno. razlika između toga što mnogi danas pričaju o slobodnoj energiji i onoga o čemu je Tesla pričao, što je Tesla do svojih tvrdnji došao posle 5 decenija, pa i više, 6 decenija, tako da kažem, jednog sistematskog, kontinuiranog, neverovatnog istraživanja u kojem je on kombinovao svoje otkrića, a mnogi danas pokušavaju nekakvim prečicama ili, tako da kažem, nekim tvrdnjama bez osnova da dođu do toga. Da li je Tesla zaista otkrio neke nove mogućnosti, iskoristimo energiju koja su oko nas ili nije, ostaje jedno pitanje za generacije koje će doći, ali ja sam samo želeo da vam pokažem i da prosto stavim to Teslino istraživanje X zraka u jedan kontekst, da pokažem šta je prethodilo i šta je iz svega proizašlo i da zapravo pokažem na koji način je Tesla zapravo jednu usko stručnu, pa za mnoge, tako da kažem, i dosadnu temu pretvorio u jednu potpuno uzbudljivu priču. Evo, to bi bila moja prezentacija. Želim još jednom da pozdravim učesnike konferencije i da vam poželim srećan rad. Hvala.
Hvala gospodinu Jovanoviću na zaista sjajnoj prezentaciji i sada vas pozivam da zajedno pogledamo izložbu u Muzeju nauke i tehnike na temu Razvoj i primjena rentgenske tehnologije kod Srba od Tesle i Pupina do danas, koju će predstaviti Jelena Jovanović-Simić, kustoskinja izložbe. Izvolite.
Pa ja bih tu razdvojila primjenu od razvoja rentgenske tehnologije. Pa što se tiče razvoja rentgenske tehnologije, mi možemo da se pohvalimo da su ljudi koji su potekli poreklom, su dakle Srbi, Nikola Tesla i Mihajlo Pupin takođe mnogo doprineli poznavanju svojstava rentgenskih zraka, takođe i unapređenju korišćenja rentgenske tehnologije. I kao što sam rekla, opet imamo proizvodnju sredinom 20. veka u Jugoslaviji, u Jugorentgenu i u 21. veku u Srbiji u kompaniji Vizaris. A što se tiče primene, tu smo, da kažem, bili dosta brzi u celom našem naporu u 19. veku da nekako na kulturnom polju i takođe na polju medicine idemo u korak sa razvijenim zemljama. Tako da već sredinom 1897. godine u Beograd stiže jedna rentgenska aparatura. Ja kažem aparatura zato što je to u stvari zaista bila aparatura više delova koji su se povezivali i koji su mogli da proizvedu rentgensko zračenje, a ne aparati u današnjem smislu reči kako zamišljamo velike aparate i kabinete. Zahvaljujući tadašnjem načelniku vojnog saniteta Mihajlu Markoviću, sanitetskom pukovniku, koji je bio vizionar i u nekim drugim stvarima i koji je brzo shvatio koliko je korisna rentgenska dijagnostika, jer su tada lekari dobili prvi put u istoriji mogućnost, znači otkrićem rentgenskih zraka, mogućnost da vide unutar tela pacijenta bez hiruškog noža i za života. Dakle, Mihajlo Marković je za vojnu bolnicu u Beogradu nabavio rentgensku aparaturu, ali se ispostavilo da je za njen rad potrebna struja iz gradske električne mreže. Kako bolnica još uvek tada nije bila elektrificirana, ta aparatura je smeštena kod Đorđa Stanojevića u fizički kabinet velike škole i dakle Đorđe Stanojević je bio čovek koji je izrađivao prve rentgenske snimke i vršio prve preglede uz pomoć fluorescentnog ekrana, takozvanu radioskopiju, a pacijente su mu ili dovodili ili upućivali lekari. Ono što je, kada se govori o istoriji radiologije u Srbiji, mnogo poznatiji i češće se spominje, jeste da je prvi aparat stigao u stvari u Šabac, iste te 1897. Mada se u ponekim izvorima navodi kao godina početka primene 899. Ali opet možemo da, mi to nismo uspeli tokom pripreme izložbe tačno da utvrdimo, da li je to ta 897. Ali je činjenica da je Avram Vinaver, otac Stanislava Vinavera, koji je bio privatni lekar u Šapcu, bio prvi privatni lekar koji je nabavio rentgensku aparaturu i ne samo to, on je lično izrađivao snimke, vršio preglede, a 1899. godine je prvi u Srbiji počeo da koristi taj isti svoj aparat, odnosno rentgensko zračenje i u terapiji oboljenja pojedinih, u prvom redu kožnih promjena, odnosno pojedinih kožnih oboljenja, zatim tumora i još nekih drugih oboljenja. Takođe je Avram Vinaver bio i prvi u Srbiji lekar koji je objavio stručne radove iz rentgenologije o terapiji i o dijagnostici, a to je bilo 1904. godine gde je izložio ta dva rada na prvom kongresu srpskih lekara i prirodnjaka. Pa nije nepoznato da se Tesla između ostalog bavio istraživanjem rentgenskog zračenja, mada tu postoji određene zablude, ali da krenemo od početka. Tesla je 1896. godine u januaru, upravo u vreme kada je i čitav svet saznao za rentgenovo otkriće, počeo, kako je sam rekao, da ponavlja rentgenove eksperimente, jer mnogo što rentgen još uvek nije umeo da objasni u vezi sa rentgenskim zračenjem, a Tesla je želeo da pronikne u prirodu i svojstva rentgenskog zračenja, kao i mnogi naučnici u svetu. Kako kažu razne izvori, u to vreme je vladala u svetu prava rentgenska manija. Dakle, mnogi naučnici su vršili eksperimente, a jedan od njih je bio Tesla, a takođe spomenuli smo i Pupin. Inače, Tesla je shvatio kada je počeo da ponavlja te rentgenove instrumente da je i on sam bio na putu otkrića rentgenskih zraka 1894. godine kada je istraživao svojstva fluorescentne svetlosti i kada je primetio da su pojedine kutije sa fotografskim pločama staklenim koje su stajale u laboratoriji udaljene od aparature za eksperimentisanje bile oštećene. I on kaže u jednom od svojih 10 radova koliko je objavio u časopisu Electrical Review između marta 1896. i avgusta 1897. Dakle, kaže, tada sam propustio da primetim ono što bi neko drugi na mom mestu možda opazio. Zatim je usledio požar u njegovoj laboratoriji i on se više tim problemom nije bavio. Dakle, šta on u tih 10 svojih radova objašnjava? On objašnjava tok svojih eksperimenata, razmišljanja i ono što je otkrio. Tesla je odmah shvatio da je neophodno da bi se dobili jasni rentgenski snimci da se upotrebi struja visokog napona i velike frekvence. A to znači da on od početka koristio svoj transformator. Inače, Teslin transformator isprobao i rentgen 1896. godine i pronašao je, i to je objavio, da upotreba Teslinog transformatora ima 3 prednosti. Da rentgenske cevi duže ostaju, duže se u njima vakum zadržava, trajnije su, slabije se zagrevaju, jer kad se zagrevaju brzo pucaju, i da se uz pomoć Teslinog transformatora u stvari dobija jasnija slika, odnosno dobijaju se jači katodni zraci i jasnija rentgenska slika. Tesla je od početka bio uveren da je rentgensko zračenje, da nije elektromagnetno, nego da je korpuskularne prirode. I ono što je meni bilo zanimljivo, to je da je on u tim radovima spomenuo da najverovatnije da postoji, tad se još uvek nije znalo za elektrone, da postoji još neka ćušnija materija, da atom može da se razloži, da on sadrži neke sitnije čestice. Druga stvar koja je interesantna i koja se obično ne spominje, to je da je on imao ideju da će rentgenski zraci u budućnosti moći da se koriste, da se snimaju ljudi na ulicama. Mi tu vidimo da je on imao kao nekakvu viziju onoga što danas je, da kažem, dosta onako i kritikovano u žiži interesovanja, a to su kamere koje se nalaze svuda po ulicama. Naravno da je tehnologija skroz drugačija, ali je sama ideja, vidite, interesantna. Tesla je uspeo uz pomoć korišćenja svog transformatora da smanji dužinu ekspozicije, znači snimanog konkretno čoveka, jer ako govorimo o medicinskoj rentgengrafiji, onda je to važno, a osim toga uspeo je da napravi snimke na većim razdaljinama, što nam je sve bitno za zaštitu, u kontekstu zaštite od zračenja. Ali ono što se ne tako retko može da čuje je to da je Tesla prvi upozorio da je rentgensko zračenje štetno. To, međutim, nije tačno. I to može lepo da se sagleda čitanjem njegovih radova. On jeste bio jedan od prvih koji je utvrdio i opisao ono što mi danas, ne danas, nego već odavno zovemo radiocioni dermatitis, dakle promene nastale na koži pod dejstvom rentgenskih zraka, ali on nije mislio da su tu te promene izazvali rentgenski zraci. Naprotiv, on je pisao da smatra da bi bilo potrebno jako dugo izlaganje rentgenskim zracima, pa i tada nije bio siguran da li bi oni izazvali promene. On je smatrao da su te promene nastale usled elektrostatičkih efekata prilikom izvođenja eksperimenata, da se tada stvara ozon koji deluje tako na kožu da je ošteti, i da se pri tome stvarala takođe štetna azotna kiselina. I upravo zato da bi zaštitio pacijenta, da kažemo hipotetički pacijent, jer su obično pacijenti, mada tu bilo ljudi koji su se snimali i u svrhu eksperimentisanja i tako dalje, on je konstruisao dve vrste zaklona od aluminijuma. Jedan je bio od aluminijumske žice, jedan je bio aluminijumski štit. To nam još jednom govori da Tesla apsolutno nije želeo da štiti ljude, sa uzemljenjem su bili ti zakloni, da štiti pacijente od samog zračenja, jer je njemu bilo potpuno jasno, a to je još rentgen u prvom svom radu opisao, da rentgenski zraci u stvari ne mogu da prođu samo kroz olovo. Tesla je znao da oni prolaze kroz aluminijum. Dakle, ono što je fizičarima jasno odavno, to je da Tesla de facto jeste primetio prilikom eksperimentisanja štetne efekte, ali ih nije pripisivao rentgenskom zračenju.
Tematske igrice za izložbu razvoj i primjena rentgen tehnologije kod Srba od Tesla i Pupina do danas su ciljano napravljene. Doduše, bila nam je ideja da privučemo mlađu publiku i da ih motivišemo i da što više aktiviramo njihovu pažnju tokom posete ove izložbe. U tom cilju mi smo kontaktirali i zamolili kompaniju Nordeus koja se bavi izradom igrica i oni su zajedno sa Krater studijom organizovali polaznike njihovih letnjih škola da tokom leta izrade dve igrice na temu pronalazaka profesora Rengena, Tesla i Pupina i da u te dve igrice ugradimo što više nekih zanimljivih stvari koje će deca upamtiti. Napravljene su dve igrice, jedna je bazirana na pronalasku njihovih otkrića i njihovih poboljšanja rentgen tehnologije u prostoru i jedna igrica je potpuno druge kategorije, ona je avanturistička, gde mladi Tesla i Teslin pomoćnik kreću se kroz prostor, tu je urađena fantastična grafika Njujorka tog vremena, na primjer, i tako. Tako da, dobili smo fantastične rezultate već odmah, povratne informacije, jer vi kad vidite dete neko koje, kad ustane s igrice, pokaže baki, bako, pogledaj onu cev tamo, to je iz igrice, to je prava stvar. I, mislim, nisu samo igrice, u principu uključili smo taj digitalni moment pored ovih vizualnih eksponata i snimali smo i VR film, nije VR film, nego samo VR, to je sam po sebi medijum, o mladom Nikoli Tesli, koji priča o svojim doprinosima i svom odnosu prema ovom rengenovom otkriću. Tu je i specijalno komponovana primenjena muzika na ovu temu iz izložbe i ta muzika je korišćena i za VR film, i za izložbu, samo web prezentaciju izložbe i za 360 foto sistem izložbe.
Ideja je potekla od mog saradnika na izložbi kao autora Aleksandra Markovića, koji je inače angažovan u PR službi kompanije Vizaris, našeg proizvođača digitalnih rentgen aparata. Ali moram da kažem da sam ja oberučke dočekala. Prvo zato što sam znala da mi na polju radiologije, odnosno konkretno rentgenologije, mi kad kažem mislim na Srbiju, imamo čime da se pohvalimo, a druga stvar je, moram da kažem da u našem muzeju, s obzirom da je Muzej nauke i tehnike posvećen takođe i zaštiti industrijskog nasleđa, se puno pažnje obraća upravo na tu istoriju industrije i u tom kontekstu mi smo imali pre nekoliko godina izložbu mojih kolega Rifata Kulenovića i Ade Vlajić o industrijskom nasleđu Srbije i ono što, eto, možda će zvučati malo onako patetično, ali moram da kažem da mene ta izložba rasplakala. Zato što sam videla da, a to je naravno nešto što znamo, ali kad vidite na fotografijama šta smo mi kao zemlja nekada imali, kakva preduzeća, kakve kompanije, šta se proizvodilo, a danas su većinom to pusta mesta, zatvorene fabrike, neke se pretvaraju u tržne centre, znači neki objekti. Mislila sam da je prava stvar da prikažemo iz tog aspekta da u nekadašnjoj Jugoslaviji, odnosno u Srbiji, je postojala fabrika koja je proizvodila rentgen aparate, kao jedina u Jugoslaviji, jedina na Balkanu, to je bio Jugorentgen u sastavu elektronske industrije Niš, a da u 21. veku, nakon svih ovih procesa tranzicije, zatvaranja mnogih fabrika, pa i samog jugorentgena, koji istina postoji, ali ne proizvodi i već 10 godina mu je blokiran račun i ne radi, mi ponovo, dakle, imamo jednu kompaniju koja je takođe jedina u Srbiji i jedina u regionu koja proizvodi ovog puta sad digitalne rentgen aparate, to je kompanija Vizaris.
Želela bih da se zahvalim svim učesnicima današnje konferencije što su podelili sa nama svoje analize, mišljenja i predviđanja. Hvala i svima vama koji ste pratili našu konferenciju putem prenosa uživo na YouTube kanalu direktorata. Nadamo se da ste nešto novo saznali i naučili iz današnjih predavanja i diskusija. Podsećamo vas da ukoliko imate dodatna pitanja za naše govornike, možete pisati na mail press@srbatom.gov.rs, a mi ćemo se potruditi da vam odgovorimo u što kraćem roku. Vidimo se naredne godine na novoj konferenciji posvećenoj primjenama izvora zračenja i nuklearnoj energiji. Prijatno!